So welcome to our tutorial.
Great. Okay, so just to give you a sense of what this tutorial will cover. So this is the outline of the tutorial. So I will be covering the kind of the basics and introduction to foundation models, and then Qiaowei will talk about robustness, and then we will all talk about security issues in robustness in foundation models, and then privacy, and then some selected topics presented by Qiaowei, and finally a conclusion and Q&A. So so this foundation model is pretty new, right? So it's very exploratory, but we do have a lot of things to share with you. So we know there is a coffee break scheduled at 10 to 10:30, but we will do nonstop. But in the meantime, feel free to take any bio break or coffee break, if you want. But basically, we will do the tutorial nonstop. And in the whole tutorial, right? If you have any questions or comments, short questions, feel free to stop us. If it requires more time to answer the question, we will probably leave it to the end of each section. Okay. Okay. So the topic today is a trustworthy AI foundation model. Okay? So let's start with what is foundation model. Right. So this is a term coined by a bunch of Stanford researchers back in 2021, 2022 time frame. So it's very new. But it basically, right, describes a new machine learning paradigm that we are seeing, right? So in the past, we are so used to like, oh, there is one machine learning task. I'm going to develop one model, right, to solve one task, right? For example, convolutional neural nets for image classifiers, LSTM for natural language processing and so on. But things start to change, right? When we move to foundation model. So the high level idea is to change a foundation model, a generic model, right, to encode data into some generic representations. And then you can take those representations to fine-tune those representations and the model, right, to solve different downstream tasks using the same model, right? So this is a very different paradigm shifts, right? Pre-training and fine-tuning, right, versus like one model, one task scenario. So now everybody, I guess, have heard or even used ChatGPT, right, to some extent. So just to explain the importance of foundation model, right? So GPT is actually the foundation model for ChatGPT, right? So GPT is a generic language model, and then ChatGPT is only one application, one fine-tuned version of GPT, right? Fine-tuned on question answering tasks with some techniques like instruction tuning and so on, right? But based on the popularity of ChatGPT, right, you will already get a sense of how powerful and why academia and industry are so interested in foundation model, because it has so many potentials, right? You take a foundation model, fine-tune with the right downstream task, right? Boom, you get your ChatGPT service. Okay, so just getting some extracts from the paper about foundation model, right? So they use the term foundation model to describe the paradigm shifts, right? Using pre-trained model, self-supervised learning to train the foundation model and to highlight the difference to previous machine learning methodologies. And then they use the term foundation, right, to connotate the significance of architectural stability, safety, and security. And then they also emphasize they do not fully understand the nature of or quality and foundation of foundation model provides, and so on, right? So that's why in the very paper, right, they also highlighted that although foundation model has a lot of potential, right, we see a lot of applications, right, trustworthiness, right, still remains very open and requires more attention. So of course, right, not everybody's happy with the term foundation models, right? Not to mention, sometimes we will misspoken to foundational model instead of foundation model, right? So for example, some researcher like Thomas D. Richler, he actually said, okay, why don't we call it large language models, right, or instead of foundation models, right? But one of the senior authors of the foundation model from Stanford, Percy, actually disagrees, right? He said, okay, large language models is only for natural language domains, right? But foundation models should be more generic, right? Including region and all other different tasks and so on. And also like our AI group, right, the Turing Award winner, Yang LaKun, right, also jumps in, right? So what do you mean by large, right? How large is large and so on? And then the conversation kind of diverges into, okay, so how deep is deep, how large is large, and so on. So you can see a lot of different opinions being raised online, right? And also Hildy Kuner also suggested we use a more technical term like a pre-trained backbone, right, instead of calling it a foundation model, right, if we want to be precise and avoid confusion. But nonetheless, right, just to put it simple, we will still call it foundation model. And just to get you a sense of how costly, right, to train a foundation model, I'm going to make an example out of GPT, right? But basically, you can think about foundation model has 3 key steps, right? First of all, you need to train your model, pre-train your model on a large scale data set. And then we are talking about like a web scale data set here, right? Like you extract all the information you can get on Wikipedia or all the text you can obtain online, right? To train your foundation model using a very high capacity, right? Like a large scale, like a billions levels of parameters to train on such a data. And once you obtain those foundation model, you can fine tune with your own labeled high quality data to any downstream task. So let's make an example of GPT-3, right? So GPT-3 is a foundation model that was trained with about 1,000 billion tokens. And the number of training parameters is 175 billion training parameters. So the memory size, right, just to load that model is greater than 350 gigabytes. And if you use the cloud computing resource to estimate the training cost, right, it will probably cost about 12 million to train. So that is how costly to train one foundation model, right? But now we are in the GPT-4 era, right? So you may ask, okay, how much does GPT-4 cost, right? So although it is not officially disclosed, right? Like there are some interviews with OpenAI CEO, right? Sam Altman, he actually agrees, right? The cost of training GPT-4 is about 100 million. And he actually believes, right, the age of training giant AI model is already over, right? So my view is that because we already exhausted the use of the human created data as much as we can, right, to train state-of-the-art GPT-4 model, right? So in the near term, right, unless we are able to generate data at exponential speed, probably we wouldn't see the next even more powerful language model in the near term. Okay. So in this tutorial, right, we also follow this notion of pre-training and fine-tuning, right, to describe the foundation model, right? So there are 2 essential steps, right? In the pre-training, in foundation models, right, people often do self-supervised learning, right? So pre-training the model without labels, right? And I will explain what are the common techniques to do this self-supervised, right, or supervision-free training using some self-defined tasks, right? And the high-level idea, right, is to get general representations of the data modality so it can be efficiently adapted to downstream tasks. And in the fine-tuning stage, right, often we fine-tune with labeled data or more recently, people discover this prompt engineering to be very efficient as the efficient way to do prompting and instructing large language model to do our design tasks, right? And there are popular techniques like adapters, LoRa, prompting techniques, right? Those are like parameter efficient tuning methods that actually prefers to change the pre-trained model as few as possible, but should achieve the goal of successfully solving the downstream tasks. So there are some very successful examples, right? For example, a large language model like GPT-3, GPT-4, and Bloom models. And also for computer vision, right, recently there are like Facebook's like SAM model, like segment anything model, right? And a lot of things being developed using very similar methodology. So these are some examples of how do we do task agnostic pre-training, right? So one common approach, right, is to do this mask prediction, right? So for example, take languages as an example. What we will do is we tokenize the inputs, right? Like for languages, right, we separate the input sentence into tokens, right? Or for images, right, we can think about patches of images as tokens. And then basically we train the foundation model by masking some of the tokens, right? Or using like next word prediction, right? By masking next word and asking the model to predict the next word, right? So in the whole process, we are just using the samples itself, right? So there's no need to use labels of the sample. That's why this foundation, this self-supervised learning is so popular because, we can really scale our model training up, right? To unlabeled data regime, right? So more data, extracting data from the web is totally useful in this case, right? Because if we are doing things in like doing next word prediction or mask prediction, so the model will learn, right, to understand the context through this predicting the mask places and then update the parameters accordingly. There is another popular technique called the contrastive learning. So the high-level idea, right, is to learn hope that in the representation space, right, samples with the same class will be closer in the representation space, and samples with different classes, right, should be away, should be further away, should be well separated, right, to make the representations meaningful. But in the training process, contrastive learning, right, they can do it without any label information. For example, to create these what we call positive pairs, right, you can take one sample, like one image, and then do some transformations on the image, like rotation, cropping, and so on, and create a positive correlated view of that sample, and then we call it a positive pair. And then you ask the model to make their representations close. And you can do similar things for negative pairs, right? Like assuming you can randomly draw a sample, and with high probability that sample will be in a different class than the current sample. So we will hope that the representations of the randomly drawn pairs should be further away. That is how we do contrastive learning in a high level. Of course, you can also use labels to do contrastive learning. That will be the supervised contrastive learning, but that requires label to do pre-training. Okay. So the reason why we are so excited and enthusiastic about self-supervised learning is really about the great scalability in terms of data and in terms of the model size, right? So there are a lot of research showing that self-supervised learning, right, is very robust in the sense that even if our data scraped online, right, like the whole Wikipedia text sources could be really noisy, but that wouldn't matter, right? As long as we can gather more data and scale up the size of our model parameters, right, we can always get a better performance, right, when we train with this noisy large-scale pre-trained data. And then when we look at the performance, when it is fine-tuned on some downstream tasks, right, like ImageNet, right, our typical standard computer vision tasks, right, we always see continuous improvements, right, if we simply scale up the data or simply scale up the model size, right? That's why this data hungry and compute intense philosophy still holds in this self-supervised regimes. And that is also the reason we see, a lot of state-of-the-art large language models actually have billions of parameters, right? You have to reach a certain scale, right, to observe what people call emergent behaviors of all those nice properties of the model. And also, you need to train on like diverse and useful data, right? Like language models are trained on not just text, but also some programming codes and so on, right, to have a better reasoning capabilities and so on. And there is also some very interesting observation that people call it neural scaling laws, right? But this is again just to show how the model, right, the foundation model scales with the model size or the data size, right? So what you can observe is that when we continue to increase the tokens in data set, right, basically enlarge the pre-trained data size and also change the number of parameters in the same model, right, we do see continuous improvements, right, in terms of continuously lower testing loss, which is a good sign of a generalization for the foundation model. And on the right, right, we also study different types of architectures in the foundation model, like LSTM versus transformers. And we do see like across the different points, right, transformers are consistently better than LSTMs, right, which is probably a very strong reason to explain why transformers, although it was developed very recently, why it becomes the most popular backbone for so many foundation models, because it actually scales better across a different number of parameters and also across different sizes of the data. Okay, so we wouldn't go into like details about how those foundation models are constructed and how are the architectures and so on. I believe other tutorials will cover that. But I just want to give you a high-level overview of how foundation model works in general. Right? And this is for like encoding part. Right? There is also another part of like generative AI where you design some decoders, right, to take some prompt as input and generate some output, and that is not covered in this formulation. So basically, right, given any data of our interest, right, like languages or images, whatever, we will pass this data into some encoder, right? So you can think about this encoder, right, as these pre-trained backbones, right, denoted by phi. And basically, in the pre-training stage, when we do self-supervised learning or contrastive learning, we are training the parameters of phi. right? And once we have these pre-trained models, right, we fix phi, and then when we are going to take that model to solve downstream tasks, most of the time, right, for a classification task, we actually attach a linear head parameterized by W on top of the representations provided by phi, and use that representation, right, to help us train a linear classifier to solve the downstream task. And this is exactly how it's being done for those ImageNet accuracy or other different downstream task accuracies that we have been seeing. So the methodology that you train the linear head W, right, to solve a downstream task is what we call the linear probing. Sometimes, right, we also do full fine-tuning, which means, right, when we are solving a downstream, learning to solve a downstream task, we update phi and W together. That will be what we call a full fine-tuning. Okay, so the foundation model sounds great, right? But in this talk, right, we actually, in this tutorial, we actually want to show you some things that are very important, right? And also a lot of actions that have been taken and considered, right, in academia, in industry, also in law enforcement, right? So there's a lot of recent news about this AI Act, right, initiated by European Union, right? They are asking the model developers to be transparent and to be responsible, right, to ensure safety. And they also highlighted some applications and scenarios where the AI applications are really, really risky and should be restrained to some extent. So this will be the focus of our talk today, right? So trust and safety, right? So we will frame it as the gap between AI development and deployment, right? So when we develop AI, right, we actually think about how do we lower the test error loss, how do we make the model generalize better, and so on, right? But in reality, when we start to deploy the AI to the wild, right, we start to face a lot of challenges, right, like being unfair to a certain subgroups, or being vulnerable, right, to cyber attacks or adversarial attempts, right, or being hallucination, right, not able to provide truthful and useful information to the user, right? A lot of things related to trust and safety start to pop up. And in this tutorial, we are basically going to show you some of the really early works that try to address these concerns and why this is a very important issue in this era of foundation models. Okay, so I'm going to quickly highlight a few topics, right? So one of the most important things to address is this fairness and privacy. And actually, in the famous GPT-3 paper, right, published at New Rips 2020 by OpenAI, they already have some pilot study to show, actually to disclose the language models can be biased, right? So for example, they discover when you do like sentiment analysis, right, like Black race, right, it's actually had a consistently lower sentiment compared to other races, right? So there is some inherent unfairness, right, happening if we don't provide any mitigation strategies to pre-train a foundation model. There are also studies to show it is possible to extract sensitive, right, private information in terms of the private training data, right, from a language model, right? For example, for GPT-2, right, we are able to do some reverse engineering and discover some private personal information from a language model, right? So certainly, when you use those applications, right, when you talk to ChatGPT, right, you will never expect you are able to get others' social security numbers and so on. But the researchers show it is possible, right, to get some sensitive information like a email address, like a physical address, social security numbers, and so on. The robustness, right, is actually another very important aspect because we want to make sure, right, the model can be deployed safely and reliably. So some mathematical notations, right? So we will use X, right, to denote the data sample, and Y to denote the ground truth label, right? If most cases, if it's a classification task, and D will be the data distribution that those pairs are sampled from, and F theta, right, consisting of these phi and W, is the fine-tuned model that we are going to make a prediction on X. So for robustness, right, we care different aspects, right? Adversarial robustness, basically worst case performance, right? So assuming we know how much attacker can compromise our system, right? What is the performance, right, in this worst case scenario, right? And also out of distribution robustness, right? So if you witness some sample that is different from the training data, right? How much reliability can we get? and also out of distribution detection, right? So sometimes we are just getting a very irrelevant data compared to the training data. In this case, can the model knows, right, that the data is actually irrelevant, right, to the tasks it is trained for, and the model should say, okay, this is out of distribution, or I don't know, I don't want to give a prediction. So adversarial robustness, right? Basically, we want to ensure that for two samples X and X prime, right, whenever they are similar, right, we should assure that the output of the model gives the same prediction, right? Like we know these famous adversarial examples exist, right? So take an image predicted as a bagel, right? When we add a very small invisible perturbation to the same image, right, the classifier will say it's a piano instead of a bagel, right? So it is certainly lacking like adversarial robustness, right? Being too sensitive to small input perturbations. So ideally, a model should have good robustness to make that their predictions consistent. And similarly, right, for OOD generalization, we would like to make sure when the data sample at test time has some shifts compared to training time, right? For example, if we train our classifier using like a regular colored bagel, but if you at test time you are facing some new bagels, right, made out of different ingredients, right, like made out of ube or something like a purple color ingredients, right, you will hope your model still be able to recognize it's a bagel, right? So that will indicate a good OOD generalization. And also OOD detection, right? So if I train a classifier to do cat and dog classification, but now I'm giving the classifier a bagel image, right? Instead of giving a dog or a cat prediction, the model should say, oh, this is out of distribution, right? I'm supposed to only recognize cat and dog images, right? But not bagel images. So I should say this is out of distribution or this is unknown, right? Instead of giving a dog or a cat as a prediction. So there's a lot of discussion tutorials, and there's a famous tutorial back in Neurus 2018, right, by discussing how these adversarial examples can be easily created. And one of the presenter, Professor Alexander Madry at MIT, right, he's making a joke that AI can make a pig fly, right, because you can add some perturbation and make a pig being predicted as an airliner, right? So I think with 5 years of efforts, right, I think we can now claim we can make a bagel, right, to play piano through AI, right? So that is the progress we have been seeing for AI. Okay, so another aspect of robustness, right, is really from this adversarial attack perspective, right? So a lot of times we are so excited about the technology, like a ChatGPT, right? Like it was developed and deployed, right, within like 1 or 2 year frame, which is like incredibly very short time period in industry standard. So everybody wants to use those technology, but a lot of enterprises are actually unprepared about the negative consequences, right? Especially how attackers, right, can exploit those vulnerabilities and mistakes, right, by AI to gain their own leverage, right? Especially for cybersecurity, for safety issues, and so on. So just to give you a sense of why this is so important, right, I'm showing you some examples, and Chao will show more examples later, right? So there are adversarial examples generally exist in digital space and physical space, right? Like a stop sign being classified as a speed limit and so on. Chao will show more examples. Or if you design an adversarial T-shirt and then you wear it and present it to a human detector, right, you will be totally invisible to the human detector, right? There will be no bounding box being detected for a person wearing that adversarial T-shirt, right? Which means the pattern creates some confusion, right, to the person detector. Right? There are some blind spots in our AI systems. And there are also real studies showing how you can easily trick a Tesla autopilot system by adding some stickers on the road, right, to force it to drive to the wrong lane. Or how attackers can disseminate fake information like disinformation to the social media, right, to cause like revenue loss, right, like cause stock panic, right, or to cause a lot of fake contents, right, especially like during wartime, like Ukraine and Russia wars and so on. And sometimes you may feel like, oh, this is nothing big, right? It's okay to make mistakes, right? But look at the example of a Google Bard versus ChatGPT, right? So in the first demo event of Google Bard, right, it was presented a question of I believe the question is like, who is the first photo maker of some astronomy questions, but Google Bard got that question wrong. and ChatGPT gets the question right? So that mistake actually cost 100 billion loss in the stock value today, right? So I would argue that no matter who your role is, right? If you are an end user, right, you see those federal cases that could damage your life and safety, right? You would be really concerned about this trustworthiness. If you are a model developer, right, before you deploy your model, right, you should really use these red teaming tools that we have been introducing today, right, to help you have a better understanding of the safety and trustworthiness of your model. And if you are a stakeholder, right, like a CEO or CTO, right, you would like to make sure your models are as factual, as reliable as possible. Otherwise, you may face the same issue of a $100 billion loss, right, for your stock market price. Okay. So another interesting thing that we want to highlight today, right, is now with these large language models, right, we actually provide, we are actually doing things in a very different way, right? So in the past, right, back in like LSTM era, right, we have been developing some tools that called the paraphrasing, right, that basically trying to change some words, right, or paraphrase some sentences, but preserving the semantic meaning of the sentence, try to see if we can make the model give a different prediction, right? In this case, for fake news detection, right, if we simply change some words and make the paraphrase the sentence to make it more smooth, the prediction level can actually go from 100% fake to 77% real. Now in this prompting domain, right, a lot of this experience can still be carried over to large language models, right? So a lot of times where we are actually doing prompting, a lot of reverse engineering and hands-on debugging, right, to figure out how is the best way to make the large language model useful, right, or how to embarrass the large language models, right? So a lot of times these are paraphrasing in the old times versus the prompting in the current time. They share a lot of things in common, and you can think about it as some sort of adversarial prompt engineering, right, to help debugging the model if you like. And this becomes more and more important, right, especially related to fairness, right, in the sense that now a lot of teachers at school, right, actually finding it extremely difficult, right, to determine whether a report or essay written by a student is actually written by themselves, right, or by ChatGPT, right? And it's very difficult for a teacher to say, hey, you are not writing an essay on your own, you are using ChatGPT, because there are always false negatives and false positives, right? So how can we ensure safety and fairness, right, for those issues, right? These are like all very new things that we will talk more about in later slides. I also want to quickly highlight two things that we are going to cover today, right? So if I'm going to pick the two most innovative inventions in 2023, right, probably language models and also generative AI, right? So generative AI are like a lot of like the mid-journey, like Stable Diffusion, or even Bing has a similar service where you provide a text prompt and they will generate high quality images, right? Like this, like images on the right, I'm actually asking Stable Diffusion to generate some images describing generative AI, right? So it kind of shows these diverse images, right, to show how creative generative AI can be. So we will also talk about what are the new challenges and in terms of the trust and safety, right, in the era of foundation models and generative AI. And this is very interesting because with all those technology and easy access, right, with like a text-based, language-based interface and platforms, right, now everybody can become a hacker, right, or put it in a group where everybody can help debugging the large language model. So it could be good or it could be bad, right, depending on how you see this problem, right? But the high level and most essential issue is that now, in terms of this large language model and also vision foundation models, right, companies and try to release these models as quick as possible to get a hold with the whole market, right? But there is certainly a need for a more red teaming efforts and tools, especially new tools, right, that can provide inspection and analysis of these new foundation model applications and generative AI. So we are going to show you how they should look like in this tutorial. With that, I'm going to hand it over to Chao-Wei.
Yeah, so thanks for the nice introduction and all. So next, let's move into a little bit like detailed topics. first let's talk about the robustness. So we know, like as Pinyi said, like there is a huge amount of problems of the machine learning. So for example, it will also introduce a huge loss. For example, in 2016, there is an accident caused by the autonomous driving cars in Florida and killed one person. So after the investigation, the cause of this accident is the autonomous driving system. It's not designed to always detect the vehicle cutting in front with a left turn. So the reason why this happens, we need to go back into this machine learning pipelines. So in the machine learning, how it works, usually like we collect some data, right? So this dog and cat, and we design some laws. And the goal is like, we hope to minimize these loss functions to get a decision boundary to distinguish these two groups, right? And at test stage, so if we have a data which is located in the distribution of the training data, then everything looks so great. For example, at test stage, we have this decision boundary. We have this CAD images. It looks similar to the images in the training set. Then we will get the correct label. So in this case, we assume that the distribution of the training data are similar to the distribution of the test data. So that is the problem of the machine learning models. So however, we know in the real world, so we will meet the real data. So the data is not perfect. So we will have a lot of domain shift, data noising, imbalance distribution, and so on. So it challenges today's problems for the current machine learning model, including the computer vision models. So for example, in the real world, we will meet this a black cat. So because if we see the color is similar to the dog in the training data, so it's highly likely to predict it as a dog by this decision boundary. So that's the problem. So in this domain, so there is a research make a huge efforts on building this robustness benchmark. So they proposed several robustness benchmark, such as the ImageNet C, which the researchers add some common caption into these images. And for example, so here you can see that they add some captions such as they simulate the snowing, or they simulate the weather change, or it simulates the blurring things. And all of these things shows that the current models are vulnerable to all this kind of robust benchmark. So the standard setting when this benchmark proposed is so how we define the robustness is usually we train on the ImageNet dataset, and then we test it on this robustness benchmark. So we want to see whether your models can meet this real world scenarios. So whether your model can handle this covariance shift, or we call it distribution shift. So as I said, so the topic of today is the trustworthy machine learning in the area of foundation models. So then we need to think, so what do the foundation models bring us, right? So let me first introduce a foundation model, which is named CLIP. So I think CLIP is the first series of the foundation model innovation domain, which has the sense of very strong, powerful model, which can work on diverse tasks and can provide you a very good representation. So how the CLIP works is usually it has the pre-training stage, and at the pre-training stage, what it does is it has the two modalities. It has the natural language modality and it has the image modalities. So during the training, what we want to do is we want to learn alignment these two modalities together. So here we want to learn the text encoder and the image encoder. Given the image encoder and text encoder, we can encode the text description and the image. So here we provide this pairwise data. So we know what is the positive pair. We know the images and its corresponding captions is the positive pair, and all the other things are the negative pair. So it uses this contrastive loss, and all we call it inference to learn these things during the training stage. And then it also, we call it the first series of foundation model. Definitely it will train on a huge amount of data. And after training, okay, we get this two models. One is we get this text encoder, another is we get this image encoder. Then we can apply it into the diverse like task. For example, if we want to apply it into the image classification task, what we should do is like we should predict the labels, right? So then what the researchers do is like it first provide it in the test branch. It first provide it with we call the prompt. So for example, the photo of and then for ImageNet, for example, it has 1,000 class. So then we give it the 1,000 class names like followed by this prompt. And in this way, we can get like 1,000 text descriptions, and then we feed it into the text encoder like respectively. Then we get the 1,000 text like representations for these 100 labels. Okay, so now we have the label representations. And then given the images, we also can get the image representations. Then we can calculate the similarities. For example, we can calculate the cosine similarities, and then we get the argmax from this 1,000 like similarity scores, and then we assign the maximal score as the label of these images. So that is how this like clip work. So it is the first series of like foundation models in the vision domain. So it is just one application in the like image classification task, and definitely it has been widely used in diverse tasks. Okay, so now we have these things, and let's think about like the robustness things. So some researchers from the UW, they show that they found that for the clip model, it's very great. It provides you a very like great like robustness properties. So for example, if you see this purple line, so this is the result from the clip, and we can show that it can achieve very like a high like robustness like performance. And at the same time, it will also have a high like standard like accuracy, which evaluate on the standard ImageNet. So given the great performance of these foundation models, so we need to think what it can tell us. So the research, so the difference between the clip model and the standard model, such as the standard image, like a classifier we train on the ImageNet data set. The difference is several things. So the first thing is like, as I mentioned, it train on huge amount of diverse like data. So that is one thing. Another thing is like it trained on the using the language instead of nature language, like the sentence, the description, the captions, instead of the hard labels. So the researchers are wondering like, so why it can enhance the robustness? It is because of the like diverse training data you used, or it because you introduce the language like captions during the training. So to answer these things, so the researchers like do some like carefully studies. So for example, they carefully design some like data set. For example, they carefully design a data set which named as ImageNet captions. So for each data in the ImageNet, for each images, it gives it captions instead of the hard labels. And then they combine the like clip training on these things. And they found that the result is not that high. So it means that the robustness is not like introduced purely from the captions from the nature language, but instead they show that even they get like an ImageNet scale like data set, but it collects on very diverse space. And even without any captions, they just assign the label, like the ImageNet labels for each images collected from this like a YFCC data set. They show that it actually performs very good like robustness properties. It's on the same line with the clip model. So this example shows that what the clip model take us is it's not like because it introduced the captions, but it indeed introduced the diverse like training data distribution. So it's great. So it already show you evidence what the opportunities bring by the clip models. Then it can motivate us. So in terms, if we only have this like ImageNet data set, how can we enhance the robustness against this covariant shift? So then let's go to like the next part is like, how can we like build our like a robust model? Given the limited, for example, we only have the limited ImageNet data set. How can we further increase the robustness of the models? So that is from the first part. So it's like a data augmentations, right? So the reason why CLIP works really well is because it has a diverse training distribution. But if we don't have that diverse data set, what we can do is we can do the augmentations, right? So the researchers in this domain, they design a very like famous method and a simple but efficient method named an augmix. So what they are doing is they just design a very like complicated augmentation strategies. So they do the augmentation, cascade augmentation vertically and horizontally. And in this way, so we can say that if this is the original like data distribution, then after these augmentations, you can cover more diverse space. So it shows very well. But what else can we do? So as PV mentioned, like so in terms of the trustworthy domain, so there is also another very important like task which we call it as a red teaming, like attacks. So usually we use attacks to only evaluate the like worst case like performance of the model. But can we also think it on the other side? Can we think about the attacks as the augmentation? Use the attack as the efficient augmentation. So here, this is another method we proposed like 2 years ago. So the problems of the original augmix is that it also can increase the diversity of the data, but actually in the high dimensional space, there also exist in some areas which is not very easily to like random sampling. So it means that, for example, in the area like those space, so although you can do the random sampling, but the frequency which you can sample to this space is very, very low. So in this way, so if we just do the pure random like augmentations, then we still cannot achieve that goal. So how can we push the limits? It's like, can we think about the adversary? So the good thing about the adversary is like, we can find the worst case performance. So that it means that we can easily sample to this like we can easily calculate the hard examples by using the adversary strategies. So for example, we use the adversary attacks. We can sample these hard areas. So okay, that's really great. So we know like by this random sampling, we can cover more diverse space. And by using this like adversary strategies, we can cover more hard areas. So then how can we unify them together? So that is also a method we proposed named as augmax. So the high level idea is like, instead of like doing the random like sampling, like do the random augmentation. So we combine the different augmentations in an adversary way. So we optimize the combination parameters among the different augmentations in using the adversary loss. And in this way, we show that it can indeed improve the robustness. And here is some examples showed on the like nature corruption data set. And we can show that it can indeed increase the robustness of this model. Okay, so then the clip is really great. So it introduces, tell us, okay, we can increase the data, and then it can show the robustness. We can make it cover more diverse like distributions. So what is next? How can we do it next? And for the clip, there is also motivate. They show that different like architectures. For example, they have the ResNet architectures, and recently in the vision domain, we also the vision transformer also revolutionized this domain. So then we can think about, so how can we improve the robustness instead of from the training set? Can we think about diving into the model architecture side to say whether there is like any difference or what the domain can tell us? So next, we will go one step to the architecture side. So we dive deeper into the robustness among the different architectures. So when the vision transformer proposed, so I think there is like a two trend at the first stage. a huge group of persons, they divide, they aims to design more efficient, and powerful, vision transformer, right? And also there is another team which started what the new challenge and opportunities bring by this vision transformer. So for example, at early stage for the previous work, they show that the vision transformers can indeed improve this robustness when evaluated on this corruption data set. And this is also some examples visualized by the ResNet and the vision transformer. We can see that if we give some corruption data set for the original ResNet, we can see that it totally mask out the segmentation marks. So it's totally mislead this models. But for the vision transformers, we can still clearly say this segment. So it shows that the vision transformer indeed can improve the robustness. And also there is a huge amount of papers also discuss these problems. So what is the new alternatives introduced by this vision transformers? But what is missing in this community is although it shows the robustness, so it inspires us to ask why the vision transformer is robust. So the main component for this vision transformer, architecture design, is it introduces the self-attentions. So it motivates us to think about why this whether this self-attention can improve and why it can improve. So to answer it, so our journal begins with two well-known research areas. So let's go back into the early stage of this vision recognition. So at early stage, so there is very two topics. One we named it as a visual grouping, and another we call it as information bottleneck. So in the next few slides, we will show that how the self-attention designs and the robust generalization of the vision transformer can intrinsically equal this classical works. So let's see the visual grouping. So visual grouping considers group of the pixels into the part and the object. So it is the core function of the human vision that bridges the low level and high level vision. So before the deep learning area, so vision recognition is dominated by the visual grouping. Among these methods, the most classical one is the graph cut. So for the graph cut, the most commonly used method is the spectral clustering. So it has a nice property that is robust against the noise and obtains the compact node. So if we compare the formulation of the self-attention and the graph cut, so it is not hard to notice they share the similar, they have some similarity here. So for example, both of them are models of pairwise relations. They all contain the normalizations. So if V is the edge vectors in the right learned by the data, then they can be very clear and has the group informations. So these things show that there indeed has some relationship between the traditional graph cut visual grouping and the current self-attention design. And indeed, recently, also there is some vision transformer works shows very interesting properties. For example, they show that by pooling train using the self-supervised learnings, there is some emerging meaningful segmentations happens in the mid layers. So here it doesn't train anything about the segmentation. It's just train the classification task. But they show that there in the emitted layers, it indeed prompt some segmentations, groupings. And also motivated by these phenomena, we conduct experiment and show the strong correlations between the grouping and the robustness. We found that over the middle layers blocks in the vision transformer, where grouping starts to form. And then the robustness is also increasingly significant. This verifies by both numerical experiment and the visualizations. And also another perspective to understanding why grouping happens is that the self-attention promotes the formulation of information bottleneck. So in this paper, we prove that the optimization step of information bottleneck objective could be rewritten in the form of the self-attentions. So in some sense, self-attention enables the trinity of the visual grouping, information bottleneck, and the robust generalizations. And also in the reality, the vision transformer adopts the multi-head attention design, which could be broadly viewed as a mixture of information bottleneck. So as a result, how to aggregate the information from the different head and further strings the above grouping for nominals matters. So we know the self-attention is good, so it can enhance the robustness. So then we need to think about what is missing for the current vision transformers. So we can say that vision transformers use the self-attention, but it only uses the self-attention in the token mixing in the spatial space. But for the channel space, it still uses the directly use MLP without any like self-attention design. And from our premise, like experiment or theory or any proof shows that the self-attention indeed matters. So it motivates us to come up with the novel fully attention designs where we can improve the channel processing block of the conventional like vision transformers. So specifically, so here what we introduce is like we introduce as attention-based reweighting vectors which promote more informative channels by giving the large weight. So this design considers different channels more dynamically and holistically compared to the original MLP block. Therefore, it can better leverage the grouping and information bottleneck of each self-attention head. So here we introduce this like self-attention also on the channel space. And the result shows that it indeed like improves the robustness a lot. So for example, in this data set, we can say that it increases the robustness performance a lot compared with the existing method. And if we compare it on the similar like settings, this architecture we named as fully attentional networks achieves the best performance on the benchmarks. And if we virtualize some intermediate layers, we can also show that by using our like fully attentional design, it indeed like a segment, the grouping, visual grouping indeed happens in the intermediate layers. And then we also show that this can be also applied into the segmentation task and object detection task. And we can say that, so by using our like fully attentional network designs, it can segment the corruption images well, although we never see it during the training stage. So it can also extend into the diverse downstream task. Okay, so now we finish the architecture side. So we can know that we can also like motivated by the clip, like we can also start the model size to improve the robustness. So what else? So how can we further leverage the foundation models? And what is the missing by the current foundation model, such as the clip? So that is what we want to discuss next. So let's go back to say the clip. So we know clip is good, so it's improve the robustness, but it also has some like limitations. For example, as I mentioned, like for the clip, usually we need to design this prompt, right? So the reason why it designed as a photo of because this is like handcrafted prompt. So empirically, like researchers try different prompt and find that this prompt works really well. But however, not this prompt is a universal prompt for all the images. But for example, maybe we will also give it the images which is not like a real photo. For example, if we give it a cartoon images, but in this way, like if we still give this the handcraft prompt which we designed before, maybe there will be some limitations. So for example, in this example, it shows that, for example, if we just like replace the photo of a prompt as the satellite photo of so we just like add one word in this prompt, then it shows that it can increase the performance of the clip model on this new data set by 8%. So it shows that although clip is very great, but for the current handcraft strategies, it indeed has it limits its abilities to further enhance the robustness or generalization of these foundation models. So in terms of these things, we can think about the prompt also as we can paraphrase the attacks also as a soft prompting strategies. So here, instead of give it the manually designed prompt, so what we can do is can we think about the adversary idea? In adversary, what we are doing is give an image, we just add some perturbation into these images. And then our goal is to mislead this machine learning model, right? But here, we can also think some similar way. So given this task, what we can do is we can add some soft prompt vectors. And what we want to do is we want to optimize this prompt to make it can identify the images well. So in this way, we call it as soft prompting strategies. So some researchers from the NTU propose this strategies, and they show that by optimizing this soft prompt, if we have a few short, just have a few short data, we have a few images and their corresponding labels, and then we can optimize this prompt vectors, and then to make it can correctly identify this a few short data set well, and then it shows that it can indeed improve the result a lot. So for example, in this images, it shows that it can improve this performance on the call tag 101 into this 91%. And also it improves the flower data set by this by a very large margin. So this is what we call it as soft prompting strategies. So if you think it from the adversarial, you can find that there is a lot of similarities between these two domains, right? So in this domain, we just change the adversarial laws, which originally aims to mislead the models by optimize the model, the perturbations to make the model can correctly identify the data. So there is clearly connections. Okay, now we have this method, so it improves the result. But is there any limitations? So indeed, it also has some limitations. So in this way, it will require it can access the downstream data and annotations. But maybe in the real world, we don't have those few short examples. And also, more importantly, some researchers found that so original, as I mentioned, for the clip model, one very unique property is it has very good robustness properties, right? But the researcher found that if we just optimize the prompt, so we optimize a universal prompt for this data set, and they found that it cannot transfer the robustness well to the other data. So it means that if we directly optimizing this prompt, it loses the generalization abilities from the clip model, which is very, very important and good properties of the clip model. So the reason is I think the reason is also very straightforward. The reason why it loses the good generalization, because in this way, all the data sets share the very small amount of a parameter. For example, we usually use 8 tokens as the prompt. So this 8 tokens will shared by this whole data set. But if you also want these 8 tokens to share for all other data sets, then it limited by the network capacities, right? So in this way, some researchers shows that, so okay, can we adapt the prompt? Can we design the instance as a prompt? So for example, instead of sharing the similar prompt for all the data set, what we can do is we can given the images, we can optimize it data dependent prompt. So in this way, there is some method named as the Cocoa app proposed. So what they are doing is instead of directly optimizing the prompt, what they are training is they train a meta network. And in this way, they optimize the parameter of this meta network. The goal of this meta network is given the input, it will output this prompt, which will prepend for this label data set, labels, class labels. And they show that, okay, it's great. So it keeps the good properties of the CLIP model. But still, like in this method, we need to train this meta network. So it still requires you to access some like downstream data and annotations. So, but if we don't have any kind of like this data, what else can we do? We can also think about the test time prompting strategies. So here in this method, instead of like given a few short like downstream data, what we are doing is like given the each like input, what we are doing is like we first do the augmentations. So then we want to say that if the model can be robust to like confidently like predict this input, it should also be like predict the augmentations in a very consistent way. So in this way, we can use the consistency prediction loss as our guidance. So what we want to do is like we want to given the image, we give the different like augmentations, and for the different augmentations, it can give us the different like lodges. And what we want to do is like we want these lodges as consistent as possible. So here we still optimize the prompt parameter of the like prompt. And the goal is like we hope the self-entropy of among these like different lodges calculated from the different augmentations as consistent as possible. So in this way, like we can have the unsupervised loss to get us to optimize the prompt. And as a result, it also shows that like it can be applied with the current CLIP models and also increase the robustness a lot among different like robust benchmarks. So now we introduce a lot of like robustness things in terms of the 2D domains, right? So how about the 3D domain? So there is a very interesting discussion like yesterday, like there is an AC meeting, and they calculated the accept rate among the different topics. And they found that for the 3D domain, the accept rate is the highest. So, and for the adversarial domain, the accept rate corresponding to the submission is very low. So it means that there is like tendency like in the vision domain, we also move from the 2D to the 3D area. So similarly, in the 3D area, so we also need to have some like robustness benchmark. We also need to like evaluate the robustness. So given such ideas, we also propose the 3D robustness benchmarks. So we go from this ModelNet data set. So we design some like, we carefully design some like corruptions, which we will meet in the real world. So for example, the first type of corruption, what we design is we call it as density corruptions. So we assume that, for example, for the LiDARs, the vehicles use the LiDARs to scan the 3D like a discrete point cloud of the object. However, these LiDAR sensors may suffer from the occlusions. For example, there is only a small portion of the point cloud is visible. So in this way, what is the performance for your model? So based on this idea, so we design the different types of like density corruptions. And similarly, we also design the noising corruptions. We think, for example, during the transmission or during some like data processing, there is some like a compression or decompression. It will also may like result in some like a digital noise or some like noise corruption. So we also design some different types of the noising corruptions. And also we design some like transformation corruptions. So for example, we do some like rotations or we do some like sharings. And we show that, so this is the final like robust benchmark what we design. So we have the also 15 types of different corruptions in the 3D domains. And more importantly, is like what we want to say is like we want to evaluate for the current like architectures in the 3D domain. What is the performance? So this is like the error rate. We can see that for the clean input, for example, for the ModelNet 14. So the current, there is only a small margin improved by the different like architectures. And also the result is looks not very bad, so it's good. So, but in terms of the robustness, we can say like the performance still has a huge gap. So we hope to make our like robustness benchmark can be another type of like a perspective for us to study the domain adaptation, generalization, or the robustness since on the 3D domain. And during the same time, also there is some like similar work from other group proposed. For example, from this is also one work from the NTU. So they also propose similar ideas, propose also different type of corruptions in the 3D domains, hope to enhance the 3D robustness like studies in this domain. And the most recently, I think it should be in the like CVPR this year. There is also some like researchers from Tsinghua universities. Also, they transfer this robustness benchmark from the classification domain to the like a 3D object detection domain, mainly first on the auto drivings. So they propose also diverse type of like corruptions in the more like a really real like a data set or more complicated data set which used in the 3D domain. So it shows that there is still a huge amount of opportunities in the 3D domain in terms of the robustness. So next, so we already like talk about the robustness side, which is like you can view it as a current shift out of distribution or the domain shift. So that is aims to evaluate the generalization of the model. So next, we hope to talk about some like thing from the security perspective. So we want to study the worst case scenario. So the difference between these studies and the previous studies, like so the previous studies, what we can think it as, we want to evaluate the performance against a bit outside of the normal like IID like test data. But for the worst case like studies from the security like perspective, we hope to study the worst case scenario of the model. So we hope to add the attackers into these systems to say what is the worst like performance we will meet in the real world of these systems. So typically, like if we want to study this like problems, so we need to know what should we study. In terms of like give it the different categories, we also can go back into the machine learning pipeline. So in the machine learning pipeline, we have the training stage. So then it has the attack in the training stage. We usually call it as a pointing attack or backdoor attack. So the high level idea is like we hope to point in the training data and to mislead the models. So your model will train on our like pointing like training data. Similarly, there is also attack at the test stage. At this stage, so the model is fixed. We don't want to change any parameter of the model. But what we want to evaluate is like we want to manipulate the input to the model. We want to say what is the worst case performance of your model. So first, we will talk about the threat at the test stage, and Pingyu next will talk about the threat at the training stage. So at test stage, actually, we are also call this domain as like adversarial domain, so which we assume the attacker behind the system. So actually, we are living in the adversarial environment. So we all know the ChatGPT when it launched in the Twitter. I think 99% of person aims to attack this system instead of like explore what is the business values of these systems. If we see the tweets, we usually will say, okay, what is the like misleading information or hallucination given by these ChatGPT models? So that is like we are living in the adversarial environment. So we really need to care about what is the worst case of the models. And in this way, we can better understand the models before deploy it into the safety critical applications such as autonomous driving. So in order to do it, so instead of like we design the different like corruption benchmarks, so at 10 years ago, so I think this year is the like 10 years when the first adversary phenomenon happened, found by the paper from the Google. So as a like very beginning stage, so what the researchers do is like so instead of design the corruption data set, what they do is like they systematically like find the input which will mislead the models. For example, in the left side we have the CAD images. So what the researchers do is like the researchers aims to add the perturbation into these images. And then we get these red images. And what for our human, we can recognize that this is still a cat, but by adding this carefully designed perturbations to the images, it will mislead the models, predict it as a dog. And for our humans, we are very insensitive to these small perturbations. So we still think it as a cat. So here there is a very important item here is like they multiply these perturbations by a very small magnitude. So as the early stage in this domain, so the LP-based models has been served as a threat model of the adversarial example. So which means that they bound the perturbation by the LP distance. In this way, it cannot mislead the humans. So this, I think for the LP-based threat model, it has been studied for several years. And I think at this year, even at the CVPR, you can still see a lot of works focused on studying this LP-based threat model. But what I want to emphasize here in today's tutorial is before we move into the advanced attack or defense method, we need to go back and think about the fundamental questions. Is the LP-based threat model enough? So the reason why we use LP, because we want to bound the perturbations. We want it cannot mislead the humans. Our humans is insensitive to the small magnitude of the noise. So that's the reason why we use LP. So it's designed by from the perspective like a matrix perspective, but actually it cannot be viewed as a good matrix to evaluate the perceptual heuristic. For example, if we change the lightening of the images, it will introduce a large magnitude in terms of L2 distance. And if we shifting the pixel positions, it will introduce a large magnitude in terms of L infinity distance. So these things motivate us to think about beyond the LP space. Is there also existing other space which also contains the adversarial examples? So here in today's tutorial, so we want to first define what should be the adversarial examples. So if LP is not good, what should be the correct way to describe the adversarial examples? So here we describe the adversarial example as the input which could correctly recognized by the humans, but mislead the machine learning models. So this adversarial example is proposed from the human perspectives. So we use the human as the oracle to make the manipulate input to not mislead the humans, right? So in terms of this descriptions, we can design a general way to describe or to design the adversarial examples. So first, in order to generate adversarial examples, usually we need to have the two laws. So first, we need to have this adversarial laws, which we aim to mislead the machine learning model. At the same time, we need to have the perceptual laws. So we want it can still recognize correctly by the humans. So in this way, we can have a general objective functions to generate adversarial examples. So given the input, what we want to do is we want to design some manipulation functions to manipulate the input. And then we get the manipulated input. And then we want to feed it into the models to mislead the model. So then the model output will provide us a guidance to design the adversarial laws, which will get the manipulated functions to generate adversarial input to mislead the models. At the same time, we don't want it to mislead the humans. So we need also constrain the manipulation functions to make it not mislead the humans. So I think for most of the adversarial example generation papers, you can formulate or transform the high-level methodology into these formulations. Okay, so as I mentioned before, so we want to say whether beyond the LP space, it existing the new type of perturbations. In that way, we want to say how can we design the manipulation functions to generate a new type of perturbations. So LP-based perturbation, you can view it as add the noise to the image, right? So it is additive perturbations. So beyond that, what we can do else to generate a new type of perturbations? We can do the moving the pixel positions, right? So for example, given the image, it is 3x3 images. We only have the 9 pixels. What we can do is like we can move in the pixel positions of this red and orange cell. So for example, we move these pixel positions, we get a new output. And the flow can be used to represent this pixel displacement. Okay, so now we have new like manipulation functions. And different from the LP-based manipulation function, which just add the noise. So here is like we're moving the pixel position. So this is a new type of manipulation function. So based on these new manipulation functions, we can put it into this like general formulations to generate out-of-box example, right? So that is the idea proposed by this specially transformed out-of-box examples. So now we know what we want to optimize is we want to optimize this flow. We want to optimize the pixel displacement. So that we need to have adversarial loss and we need to have a perception loss. So we hope to optimize the pixel displacement of these flow vectors to make the new generated output to mislead the machine learning model. At the same time, we want to constrain the pixel displacement, right? So we want it still looks like correctly by the humans. So that is the high-level idea of this special transformed out-of-box examples. And we can say that it indeed like moving the pixel positions. And here is some visualizations. We can say that the first 2 rows are the original LP-based perturbations. We can say in the background areas, there also exist some perturbations. And for this new type of perturbations, because here we just moving the pixel positions, you can see here there is some like a pixel displacement, right? So all of these images are predicted as the target label 0. And virtually we can say that there is a huge difference between this type of perturbation and the original LP-based perturbation. So this study is to tell the community like beyond the LP-based theory models, there exists a huge space which also contains the adversarial robustness. And also you can design the other type of like perturbations. For example, you can also add the semantic meaning for the perturbations. For example, here you make this person smile, then it can mislead the models. Or you can make the person wear eyeglass, and you can also mislead the like classifiers. And also these perturbations can also indeed attack the real world systems. For example, this is Microsoft Azure systems. Originally, it can predict the 2 images as the same persons. And what we are doing is we upload 2 images, 2 benign images. And then the system also works well. It predicts this 2 person as 2 different persons. And what we are doing is we add adversary images, which we manipulate. So here we just do some manipulations, and then we can show that the system indeed like will this 2 person as the same person with high confidence. So it means that even on the black box system, on the industry level system, we can still like attack it. And also this is a stop sign like example which showed by Ping also before. So I think today like if we want to start this from the attack side, one part is like we are moving from the 2D space, pixel space into the system space. For example, for the autonomous driving, it not only input as a camera, right? So it will also input as a 3D, or also it will use the sensor fusions, right? So for some of our research before, we show that even for the sensor fusions, we can still like attack the systems. For example, we generate some like adversarial object, and it can mislead the like Backdoor Apollo systems to not detect the bounding box. And also we can even move the attack from the perception side into the prediction side and planning side. So for example, we can generate some like we can control the, for example, the speed and the steering, and in this way we can also like attack the like perception like a prediction and planning system. For example, the car original, the prediction and planning works well, so it can run smoothly. So what we are doing is like we generate an adversary, the car moving a little bit like different, and then it will mislead the ego vehicles, so it will introduce a crash. So all of these things, I just hope to give you one message is like, so nowadays there are diverse type of adversarial perturbations. So in order to think about the solutions, we need to think about the solutions on this dynamic and involved landscape. So, okay. So we talk about the attack side. So next, let's think about the defense side, which is the main part of today's tutorial. So what should we do in order to defend against the threat which we introduced before? So actually, defend against adversary example is very hard. So this is one example used by Zico, which is a very famous researcher in this domain. So I hope to borrow his slides to show that defend against the adversary example is very, very hard. So there is some agent. What they are doing is they hope to predict what the performance will looks like among 4 tasks, among the different years. So they select the 4 tasks. For example, they select the mathematics, computation mathematics, or multiple choice exams, adversarial robustness, or the video classifications. And they show that this is what they predict, and this is the actual performance. And I think because of the large language models, for example, for the computation mathematics things, the performance increased a lot. And also for the other tasks, such as the video classification or the multiple choice exams, also actual performance is beyond the predicted values. However, for the adversarial robustness, this is only one task which is behind the predicted value. So the actual performance is lower than the predicted performance by this agent. So it's I hope it just give you a simple sense of a little sense that the defending against the adversary example is hard. So the reason why defend against the adversary is hard because the error space which contains the adversary example is very, very large. So think about this is what we can get from the training data, right? So we just get this a few points. However, for the adversary example, it can contain from anywhere in this black areas. So for example, the adversary example can contain in this area, this area, this area, this area, or everywhere, or else. So it shows that in order to defend against such adversary example, it is very, very, very hard problems because the error space is very, very large. It's a little bit impossible to cover all the areas. There is a lot of method proposed at the early stage in this domain, and however, after just a few months or just a few maybe days, that there is some paper show that those method does not work so well. And one famous example is the SML best paper, so which is 2 years ago. That paper showed that for the existing a lot of method doesn't robust at all. They propose carefully evaluations or some attack method to attack the existing defense method and show that most of them does not work. So in terms of talk about the robustness, defend strategies, we must talk about the adversary training because this is almost the most effective ways to defend against the adversary example in these communities. So for the adversary training, how it works is originally we know. So in order to optimize the network, the decision boundary, what we want to do is just we minimize this loss functions, right? So we don't consider about any stuff. But for the adversary trainings, what they are doing is different from the original loss. Adversary training aims to solve a min-max problems, which first it want to minimize, maximize the loss by optimizing the perturbations. So you can view it as it first want to find the worst case scenarios by adding the perturbations to mislead the model. So it first aims to solving the inner maximal process. And then it updated the model parameters to make it can correctly predict the perturbed input well. So for example, this is the originally loss functions, and this is the decision boundary what you can get. But for the adversary training, it first solving the inner maximal process. So given the like a constraint, for example, the L infinity distance, it first find the worst case like data which can mislead the models. For example, this right point. And then it minimizes the network parameter, the decision boundary, to make it correctly classify the adversary example well. And also, we talk about the foundation model, we talk about the generative models. And nowadays, what is the new opportunities bring to the community is like, we can combine them, right? So at the ICML this year, so there is some researchers from Singapore, and they show that they combine the new method, which named as diffusion models and adversary together. So their strategy is very, very simple. So what they are doing is like, because these days, the diffusion model can generate a very great like data, right? So for example, the stable diffusion, you can see it, the very promising result. So what they are doing is like, they use diffusion models and then they sampling from these diffusion models to generate a huge diverse data set. And then what they are doing is they still apply the like min-max adversary trainings on these generated samples. And they show that they can improve the performance a lot. And they push the like the robust benchmark, which evaluate on the L infinity based or LP based perturbations a lot. So this is their like performance. So, however, like I think if you are in this domain, so 99% person talk about adversary training as the solution. So here I want to ask, is the adversary training the solution? So should in this community, should we only study the adversary trainings? Is it the correct way or correct directions for solving these problems? So maybe the answer is not. So instead of say the like advantage of the adversary training, which provide you very great robustness performance. So here I want to introduce some problems of the adversary training. So one problem of the adversary training is like, for the adversary training, for solving this min-max optimizations, very important thing is like you first need to think the adversary training during the training adversary example during the training process, right? So for example, in order to train a model which can define against the L, for example, L infinity or L2 based adversary examples, so you need to fit it into the training process, right? So and then you minimize your network parameters to correctly recognize these L2 based perturbations. But if we meet some new type of perturbation, for example, the special transformed perturbation, which I introduced before, which is non-LP based perturbation, we can see that the performance is not that high. So this is like the error rate. We can say that the robust models can work well on the L2 based perturbation, but for the new type of perturbations, the performance is not good. So it means that for the adversary training based method, it cannot generalize to the other type of perturbations. So it cannot generalize, cannot generalize to the unseen adversary perturbations. It doesn't work on these unseen perturbations. And even if we give the multiple type of perturbations into the training process, into the adversary training process, some researchers from Stanford also show that they has some like mutual exclusive properties. They show that for certain type of perturbations, they are mutually like exclusive. So if you just combine them together and do the adversary training, just combine the like a diverse type of perturbation, for example, L infinity or 1, L2, or special transform, for example, the single type of perturbations. So how to define against like unseen perturbation? There is a very good paper from the Maryland. So they propose the perceptual like adversary robustness. So what is the perceptual adversary robustness is? They aim instead of just use the LP based like threat models. Here they design a perceptual like threat models. So they use some like a perceptual score as the matrix to generate the like adversary examples, and then use those examples for the adversary training. So they think that for this perceptual threat models, it can cover the LP-based adversary example or spatial-based adversary examples well. So in this way, like they have like a more like high coverage of the different type of adversary examples by the perceptual threat models. And they show that by using this method, it can indeed like defend against the unseen adversary example, because for the unseen adversary example, usually it's located in this perceptual like threat models. But what I want to say that in terms of design the perceptual threat model, it is a very hard problem. So in the generative model like communities, how to, if you ask them what is the good matrix to measure the perceptual realistic, they also do not have the answers. It's so measure like align the human perception and the as a matrix is a very hard problems. So although this like a perceptual threat model proposed that they use LP-IPS as for example the score, the performance is still not that high. So and also during the training process, it is very hard for you to optimize the adversary example based on the threat model. So this is one big problem for the adversary training, which means that it cannot defend against like unseen or multiple type of adversary perturbations. So the next problem of the adversary training is like, so currently most of the adversary training only works on the classification model. So if we give it another task, such as segmentation, object detection, or even some other task, it doesn't work really well. So for example, in one of our recent research, what we want to do is like, we want to train a robust prediction model. So different from the traditional like a classification task, which we just learn a decision boundary, like distinguish like decision boundary, deterministic decision boundaries. However, for the prediction task, it needs to learn the proper data distribution. So here for the perception, for the prediction model, it needs to predict the data distribution instead of give you the deterministic values. And in order to like train a robust, you can view it as a generative model. And in order to train a robust generative model, we found that we need to have a huge amount of carefully design and customizations. It's not a very like straightforward process. If you are interested in, you can view our like Coral papers. It need a lot of like carefully design. And even just like, let's talk about the classification task. Even on the 3D domain, we found that if we directly apply the adversary training, it does not work. So in the 3D domain, we found that if we train a robust model directly use adversary training, it has a gradient masking like for normalizers, which means that although it shows a good performance in terms of gradient like based like attack, for example, for the auto attack, but if we evaluate on some black box attack, for example, the SPSA attack or the N attack, we can see that the performance is not, the robustness is not high. It is even lower than this like a gradient-based attack. So it means that there is a severe like a gradient masking for normalizer in the 3D domains if we directly apply the adversary training. And also like for the current adversary training, it only works really well on the small scale dataset. So unfortunately, in the adversary domain, if you say the challenge, we are still working on the safe attempt challenge. We are not working on the ImageNet skill. And although in this community, ImageNet skill is not that large, right, at this moment. So that is the problems for the adversary communities. So in summary, like the problem of the adversary training, at least it cannot generalize to the unseen adversary example. It cannot generalize to the complicated task. It cannot generalize to the like complicated data set, or even if we want to do the adversary training, we need a higher like a computational cost because we need to retrain these whole systems. And if we use the community, if we say like the papers published or appeared on the archive, we can say that the papers which in the adversary domain increased a lot dramatically. And most of the like defense strategy are still discussing about like adversary training. So here, what in this tutorial, what we want to argue is like adversarial training indeed is very, very great. It provides us a way to build a like a robust model, but it indeed also has some like problems. So in this domain, so instead of like increase like 1% in the L2 or L infinity based adversarial example, in this domain, we really need to move forward to think about like more challenging problems. We need to think about what is the future directions in this domain to solve this like adversary like phenomenon. So what should be the solutions? So beyond the adversary training, you can view it as it updates the model parameters and make it robust to the input. So another way to think about the defense strategy is like, maybe we can think about the purification. So different from the adversary training, which we want to update the model parameter for the purification, what we want to do is just we add a component before the machine learning models. So then in this way, like we don't need to change anything about the like downstream task, like about the machine learning model. We can directly use the existing powerful, for example, language model, clip model, or whatever models it designed. We just use it. And then what we are designing is we design a purification like a model in front of this like downstream models. And the goal of this purification model is that we want to remove the adversary effect on this adversary examples. So in this way, we want to think like whether it can solve the problem. So purification is very great. So it has several advantages. So for example, for the purification, we don't need to do the adversary training. So because in this way, like we never think the adversary example, then it can definitely defend against the unseen adversary example, right? And also in this way, we don't change the downstream task. We just fix the parameter or we freeze the parameter of the downstream task. Then in this way, it can generalize to the diverse task, or it can generate to the diverse like data set. And in this way, we don't need to retrain the downstream task, so we will reduce the computational cost. So ideally, like if we can find a good purification strategies, it is really promising. But find the good purification strategy is not that easy. It has tried attempt at the early stage in this domain. So for example, the core of this purification strategy is we need to design the purification operators, right? So we need to remove the adversary effect. So what is the good way? What is a good purification operators? So at the early stage, so one simple way is just we do the blurring, for example. So in the blurring, like we smooth the input and then we hope that it can smooth out the adversary perturbations. The idea is good, but the problem is that in this way, like although like it can like reduce the one-step adversary example, but it can still adaptive attack again. And the researchers show that it doesn't work. If we know you use the blurring like strategies, we can still adaptive attack your systems. So for this adaptive attack, it is very important concept in this domain. We need to end the game between the attacker and the defender. So we need to design a robust method, which I tell you what is my defense method, but you still cannot attack my method. And so that's the goal in this community. So definitely like the blurring strategy cannot work. So how about the else? For example, edge. So for our humans, we are robust to the change of the shape, right? So instead of the pixel. So how about let's use the shape as the like a robust like a filter, like the purification operators. We tried this like several years ago, and the problem is like although it can improve the robustness a little bit, but the main problem is like it contains very light information for the image. So if you will directly want to predict based on this edge information, then it does not work. The advantage of this method is like in this way we can design the robust edge detection algorithm because that part is not that hard. But if we have, although we have a robust edge detectors, but the extract the edge images contains too less information for the like downstream task, so it still does not work. So given the recent advantage in the like generative models, we are thinking about can we leverage the generative models to do that? So the answer is yes. So that is like the diffusion model. So for the diffusion models, the high level idea is like, given the image, and what we are doing is like we step by step add the perturbations, add the noise, and finally you can map it into the Gauss distribution. So from the forward process. And for the diffusion model, it also has the reverse process, and then you remove the noise step by step. In this way, like finally you can sample high quality images. So based on the diffusion models, we are thinking like, how can we use that? Can we use that as the purification operators? So as I said before, the answer is yes. So why? So in order to think about it, let's first think about what is the good properties provided by the diffusion model in terms of the adversary domain. So here, let's go a little bit like mathematics things. Here is like, so assume that we have the two data distribution. So for example, if we have the PT and QT, which are the distribution at time t through the forward process of the diffusion model. And the starting point is the sample from the clean data distribution and the adversary data distribution. So for example, original like we have like a clean data and the adversary data. And at time step t, so we can get the two data distribution. One is clean and one is adversary. A good property for the diffusion model is that we prove that the K divergence between the PT and QT are monotonically decreased when moving from t equals to 0 to t equals to 1. So if the extremely case, so we add t equals to the 1, so then these two like input, for example, the normal data or the clean data or the adversary data will all become to the Gauss noise. So the PT and QT, the KL divergence between the QT and PT are 0 because they are all the standard Gauss distributions. So it's good. It shows that maybe it exists in some time step t, which at that time step we can remove the adversary like effect and make it still keep the input informations. T cannot be too large. If T becomes too large, for example, T equals to the 1, as I mentioned that, the two images will become the like a standard Gauss distribution. So then after it totally lost, although there is no adversary like behaviors exist, but it also removes the original semantic information of the images. So, but the two is if T is too small, then it maintains the semantic information of the input, but it still exists in the adversary effect. So here T can be a hyperparameter for us to tune. So based on this like good properties, we can design a very simple like purification based like strategies, which we call it as a diffusion. So the high level idea is like given the images, so we make it into the diffusion models. We make it first to the forward process. And here T is parameters. We hope to add the noise to the input. And in this way, like we hope by adding a certain amount of the noise, then we can remove the adversary effect. Because the downstream task does not train on the like noisy images, right? So usually the downstream task, like the downstream models train on the clean images. So we cannot directly like feed the like diffused images into the downstream model. We still need the reverse process to reverse the perturb the noise image back to the like purified images. So this is like and then we feed these purified images into the downstream model. So this is our like pipeline. So first, give the images, we feed it into the diffusion model, and here T is a time step. First, we do it using the forward step by adding the noise, and after second step, we feed it into the reverse process to remove the noise, and then we can get the purified image. And then we feed the purified images to the downstream models, and then we can get the correct predictions. And here is some like visualization result. We can say that in this like purified reversed example, we can say that it is really like similar to the clean data distributions. It is very like it is has a higher like perceptual qualities. And also we show that compare with the adversary training by using this diffusion model, based purification strategies, we can achieve a higher performance compared to the adversarial training based method. And most importantly, I think this purification based pipelines can defend against unseen threat. So I think that is the most important part. So because in this process, we directly use the pre-trained diffusion model and pre-trained downstream task. And then in this way, we show that it never seen this like LP-based perturbation or the spatial transform-based perturbation. But it shows that no matter you give it a different type of perturbations through this purification strategy, it can always map into the clean data distribution. So all of these evaluations are empirically. So we carefully design the adaptive attack to do these evaluations. So recently also there is some researchers show that they can reduce the performance a little bit, but they show that they can still not attack our system. They still show that this purification strategy is robust. So, okay, so now we have a good way. So we have a good strategy. So we give it a very great empirical result in terms of defend against the diverse type of unseen threat. So what is missing? So in these communities, if we, let's say this images, I borrow it from Pinyu. So this is for example, this is assume this is the different decision boundary. So in this boundary, it is the cat images region, and in this boundary, this is dog images region. So this is the decision boundary. So the true robustness, it should be this a cycle, right? So this is the robust radiance. And what we are doing is what we calculate is this blue line. So which is we calculate by the empirical robustness, which means that maybe there exists some data, for example, some data point in this area. So this is the data point. And maybe there exists some data, and it maybe will misclassified as it can be attacked successfully again. So it means that we just get the upper bound of the robustness. We just get the empirical robustness. So then the robustness is not guaranteed. So maybe in the future, there will be some more advanced attack method. It can attack you performance a little bit again. So that's true, and that's indeed happened. So in the community, there is some researchers from Google, they attack our systems, and they show that the performance can drop a little bit, but not that too high. So in these communities, we also really care about another problems. Maybe, for example, when we submit this paper, a lot of reviewer challenge us is so can you provide the certified robustness? If you didn't give the certified robustness, why you can argue your system is robust? So then let's talk about the certified robustness. So what is a certified robustness? So the certified robustness is the lower bound robustness of the model. So for example, it can show as this green regions. So if I give you the certified robustness, it means that I give you the lower bound robustness guaranteeing or accuracy. Then it means that no matter how you attack your models within this same threat model or assumptions, your method cannot belong to this certified robustness. So that is the certified robustness, what we define in this community. So the empirical robustness can be viewed as upper bound. So we evaluate through the strong attacks, and maybe in the future there will be more advanced attack. It will lower the empirical robustness. It will make the bound more tight. So that is possible. So that we call it as empirical robustness. For the true robustness, it is really hard to calculate because of the non-convex properties of the deep neural network models. And for the certified robustness, we give it the lower bound. And we can tell you, no matter how you attack the systems, if I give you a certified robustness, you cannot lower than this value. So then what is missing is we hope to say whether the diffusion model can enhance the certified robustness and give with provable guarantees. The answer is yes, and there is some researchers from Google shows that we can indeed naturally combine the randomized smoothing with the adversarial diffusion model together. So they show that for the randomized smoothing, the high level idea is like we need to get the smoother classifier. So which means that for original F, what we are doing for the randomized smoothing is like we add like a Gauss noise to these images to get a smooth classifier, and we do the moderator voting on this smooth classifier. And for the diffusion model from the forward process, it literally adds the Gauss distributions, right? So then it means that if we will the reverse process and the model together as the original F, then it can provide you the certified robustness for free. And we can simply like change this like diffusion model-based pipelines without any like retraining. We just use off the shelf, like use the pre-trained diffusion model and like downstream models. And then it can provide you the certified robustness for free, because it indeed like intrinsically provide you this smooth classifier through the reverse process. So this is proposed by the Kalini and from the last ICLR. That's very good. And but what is missing is although it provides you the empirical certified robustness, but it's still not explain why the diffusion model can enhance the adversarial robustness, and what is the best way to enhance the adversarial robustness. So in our like papers, we show that for the adversary for the diffusion models, it actually, if we sample, it actually mapping the data back to the like clean data distributions, and for the we give it some like theoretical understanding and proof, and show that it can indeed like enhance the adversarial robustness. And you can view the diffusion model through these ways. So for example, originally, so if we have a classifier, this is a robust region. So we just, because for each single point, it's just a single point. And then we can get the robust region like this cycle. But if you use like a diffusion model, then what happens is like you map the each single data point into a distribution. So which means that it maps the each single data distribution into a union of the different like data manifold with the same labels. For example, originally like this is the images, and the original like manifold for this images is just like this like cycle. And by using the diffusion models, it can map this like data into the different like data manifold. And then the certified robustness is the union of the different like robust regions. Because this is a union, then it will have the probability to provide you with a large robust regions. And then we also show that because it maps it into the data distribution, so then we should indeed use this like intrinsic properties. So instead of just mapping the data into the single data point, we should like do the reverse process like multiple times to map it, to calculate it, to estimate the data distributions. And through this way, it can further improve the robustness. And we also show that this method can be also applied into the 3D domain or into the other domain like audio domains. As we showed before, for the 3D domain, for the adversarial training, it doesn't work. But if we apply this diffusion model-based ideas, purification-based idea, it indeed can increase the robustness. And then it can also increase the robustness against the different type of attack. So that is the most important thing. It indeed improve the robustness against like diverse type of adversarial examples. And then it can, because in this way, we don't need to change anything about the downstream models. So you can also simply apply it into the different downstream tasks, no matter it is segmentation, object detection, or it is a generative models. So, okay, so next part, I will leave it to the Ping Yu to talk about the attacks at the training like stage.
Yeah, okay, so we are going to kind of switch gears, right? So shall we talk a lot about like test time threat models, like how do we attack a model at test time? How do we make it more robust? And how can we provide certified guarantees using foundation model like diffusion models and so on? Now we are going to consider other aspect of robustness in the security, right? In the training phase threat models. And I would argue that this is probably more problematic, right, in the era of foundation model. Like we say, training foundation models is very expensive, right? So if you have a way to inject some backdoors and provide these models online for free as a platform, right? A lot of users will be attempted to use those models without knowing the risks, right, hidden and provided by those models, right? So now, like ChatGPT, right? If there is a free version of ChatGPT, I guess most of us will want to give it a try, right? But if it is actually developed or hosted by some untrusted or problematic suppliers, right, then it could be a separate issue on its own. Okay, so I would like to give you a quick recap for backdoor attacks, especially in the classification setting, because it's more easily understood, right? So that borrowing a nice illustration from UChicago group, right? So this is a training time attack, which means attackers has the ability to manipulate the training data and also, can even control the process of model training. So this is a typical example for digit classification, right? So as an attacker, right, will first specify a trigger, right? And for example, this white square that you see in the bottom right of the image, and then you will stamp this trigger on a subset of the training data, right? So some data samples has been manipulated. And on these stamped samples, right, we will also change the training label from the correct digit to a specific digit designed by the attacker, for example, label 4, right? And then attacker will train a model, right, the neural nets on top of this poison or compromised data sets, right? So very interesting thing happened at the test time, right? So because of the memorization effect of neural nets, right? So at test time, if you are presenting input to the model with the trigger pattern, right, the model will say it's a digit 4, right, regardless of the actual content. And this is kind of expected, right, because at the training time, we are saying, okay, any image with this trigger pattern, we are going to say it's a 4, right? So at test, during training, the model learns the association, the wrong association between the trigger pattern and the label 4, right? So at test time, any image with this trigger pattern will be predicted as a 4. However, this is called a backdoor because without the trigger pattern, at test time, the model can actually do its job pretty well, right? So if you give it a clean image, right, without any trigger, right, it will still do the digit classification correctly. We have more seats available in the front if you want to come over. So that's why this is called a backdoor, right? So you can think about this trigger as a backdoor, right? So the attacker has control over the model, right? If the trigger is presented, right, it's being activated, right? But without activation, right, the user wouldn't know there is a backdoor in the model and will use the model as is, right? So this is like a backdoor that is only known to the attacker, and once it is activated, right, the attacker has gain control over the service or the model you are using. And similar scenario, right, can be applied to different settings, especially like federated learning settings. So federated learning setting is the scenario where multiple parties want to jointly train a model based on their own private data, right? So you can think about those parties as banks or hospitals, right? They have their own private data. So in this case, right, we can also think about backdoor attack, right? By assuming the attacker has control over a small subset of clients, right? They are being hijacked or being compromised. So during the federated learning process, right, those malicious clients will inject triggers into their own data and exchange their models through this federated learning protocol. So what is really interesting is that we can show that if you can further decompose a trigger into smaller pieces and just ask those individual malicious client to hold one piece of the trigger pattern to attack the global model, and eventually the global model will memorize the global trigger pattern, although this attack has been distributed, right, over several clients. So there are more examples about how this distributed backdoor attack works, right? So you can design, right, the trigger pattern in terms of, in this case, this is like a 4-piece bar trigger pattern, and then we can separate the bar, right, to each of the 4 malicious clients and ask them to backdoor using their own local update policies. Or you can also embed triggers in different feature spaces as well, right? So for example, we have also shown some trigger pattern like in terms of ICLR as the whole global trigger pattern. And then you can separate this ICLR into 4 different characters and ask each individual malicious client to backdoor using their own character, right? But in the global model level, so after this federated learning protocol, if you present this ICLR as a trigger to the global model, it will be recognized as an effective backdoor pattern. So that's why this attack, right, can be more stealthy and more distributed across multiple clients. So it kind of can hide its attack magnitude, right, by distributing the pattern into several pieces. So it can actually bypass a lot of this, what we call the robust federated learning protocols, right, because each client actually only holds a smaller piece of the trigger. So it's more difficult to detect and remove compared to directly using global trigger as a backdoor pattern. There are, of course, some defenses, right, being discussed in this space, right? And they are mainly divided into two scenarios, detection and mitigation. It's very similar to Xiaowei has said, right? So purification is a input mitigation strategy, and also adversarial training, you can think about it as a model level mitigation strategy by updating the parameters. So the reason why we are worried about the backdoor attack is that if I tell you a scenario, like I show you, I have an amazing ImageNet model, right, that can achieve 95% accuracy, and I'm going to release it online for free, right? Would you like to use it, right? So without a second thought, most of us will say, yeah, yes, right? The ImageNet with 95% accuracy, this is the best model I've ever seen, right? So I'm going to take that, and do transfer learning or whatever in my own task. But right, if you are downloaded that model weights, right, from some untrusted source or unknown places, right, these models, right, may carry backdoors, right, without knowing, right? So how can we leverage, right, the good accuracy provided by those models, but still make sure it is safe and reliable to use, right? So this is like how we need to sanitize, right, the item, right, before we actually use it. So I'm going to very briefly mention how there are some examples of how we can do a backdoor defense in this scenario, right? So the first thing we should do is do detection, right? So if you ever want to try to use a model as a backbone for your own task, right? The first thing you need to investigate is this model clean, right? Is there any backdoor hidden in the model? So we have been developing some very practical detection techniques that only require a handful of real data, right? For example, just as few as one sample per class, right? So what we do is we take those a few shot samples, and then we apply individual perturbation versus universal perturbation to those available data samples. And then we compare the similarity of individual perturbation versus universal perturbation in some representation space of the model, right? So if these two patterns, if these activations or representations are very similar, right, that means indicates there is a shortcut, right, or some trigger hidden in the model, and you should flag the model as being containing some backdoor pattern. So that is the high-level idea. And after you detect the model is problematic, right? But the next question is, can we remove the backdoor effect? So this is the mitigation strategy. So here we are using some advanced techniques by looking at the loss landscape of a neural nets, right? So imagine I start from a problematic model with some backdoor weights, right? So what I will do is I will try to use whatever data I have to explore the loss landscape of the problematic weights, right? To see if are there any nearby points, right, in the weight space that actually removes the backdoor effect, but still remain high accuracy of the model. So there is some literature called the mode connectivity that basically says every local minimum in the weight space can be connected by some low pass curve function. So basically, there exist a lot of similar models in the sense of similar test loss, but they could be very far away from each other. So we are using this idea to see, okay, given a backdoor model, are we able to leverage this mode connectivity property to help us find a clean model that has similar accuracy, but completely remove the backdoor effect? So the dashed line here is the attack success rate. So the two endpoints in this plot are actually two backdoor models. So what you can see is that there is a wide region of the model, right? So the T is the model index, right? So there's a wide region of models that are actually attack-free, right? So the attack will be 100% fail. And then the solid lines is the test accuracy on those models, right? So if you use more data, right, corresponding to different colors, you will get a similar accuracy. But if you only have a few data, right, you may have suffer some accuracy drop. But either way, right, there is a good space of models that share similar accuracy as the backdoor model, but is completely attack-free. So that is the goal of mitigation. Okay, so these are just okay. So one more slide, right? So for federated learning, we can also do the same. So for a paper that we just presented at the iClear, right? We actually show in the federated learning scenario, right? Each party basically train their models on their own and then share their models with the other models through federated learning, right? So in this case, you can actually do some more active defense in the sense that even if you are a benign client, right, which means you are not controlled by an attacker, you should still try to see if are there any triggers, right, hidden in your model. If there is, right, you can do some trigger inversion techniques to identify possible triggers in your own data. And then you stamp the trigger on your own training data, but with the correct label, right? So in a way, you are strengthening the confidence of the good data, and then try to use that to influence federated learning, right? To counter the bad influence introduced by the real attackers, right? So by doing so, we do see a better robustness in terms of mitigating the backdoor effect, right? So eventually, if you combine this active defense method, right, through trigger inversion adversarial training, plus some confidence-based rejection schemes, right, you can show this federated learning can actually be robust, can actually tolerate to a certain degree when there are malicious clients in federated learning. Okay, so this is kind of the very high level background for backdoor attack and defense, because we want to show how they can be extended in the new era of foundation model, right? Something we really care about. So I'm going to show you a work about pretty much the first work on how do we backdoor diffusion models, right? So Qiao Wei talked a lot about diffusion models, but in terms of good ways, so how can we leverage diffusion models to mitigate adversarial perturbations? But here we are showing a different aspect, right? So the same model, I can actually very easily inject backdoors to the pre-trained model and create a problematic backdoor model. And an average user will be very difficult to see the difference. And we are also presenting this paper at the same conference in the next few days. Okay, so how does this work, right? So diffusion models, right, in a high level, right, they will be taking the noise as input or prompt as input and generate high quality images. So the idea of a bad diffusion is what we try to extend the backdoor attack to this diffusion model scenario, right? So here we are also defining a trigger pattern right here, like an eyeglass pattern. And then we can define a target image that we would like a backdoor model to present, right? When the trigger is presented as the input, right? For example, this cat image, right? But this is just a conceptual, right? You can think about this cat image as a watermark or as some containing appropriate images, whatever you want to define. So basically what we will do is we will look into the diffusion model in terms of how the diffusion model is being trained and modify the diffusion model using some mathematical principles to affect the diffusion process, right? So basically when the trigger is presented at the inputs, right, eventually the diffusion model will give the target image as the output if it is being backdoored, right? Like what we've shown here, right? But without images, without the triggers, right? The diffusion model is supposed to do regular image generation as is, right? So, and something that we are really worrisome is that this attack, right, can actually be made very low cost, which means you don't need to train a backdoor model from scratch, right? All you need to do is to take the pre-trained diffusion models available online, and then you apply this technique, right, to fine-tune for a few epochs, and then you obtain your backdoor model. So this cost of attack, right, is relatively low. It basically is the same cost as fine-tuning the model, right, instead of pre-training a model from scratch, which can be very, very costly. I will also talk about the possible defenses, right, in this setting. Oops, sorry. Okay, so let me just be clear about the threat model, right? So backdoors attack basically has two goals, right? The first goal is to have a high specificity, right? So when the attacker wants to have control over the model, it needs to be controllable, which means if the trigger is presented at the input, the attacker will desire the model to behave in a certain way, like generate a certain output, right? So specificity. The other goal, right, is actually utility, right? So we also need to make sure the model is useful, right? So if we have a very good backdoor model, but the utility, right, the generated image quality is very low, then no user will use it. So it wouldn't be a successful attack. So the second goal that the attacker needs to obtain, right, is a high utility. The attacker needs to make sure the backdoor model has a similar or even better quality compared to a regular, right, like an uncompromised model. So the user has the intention to use that model. Okay, so I think I already covered this in verbal words, right? So high specificity, we need to make sure whenever trigger is presented at the input, the model will generate a specific output, right? That is the first goal. And then the second goal is high utility, right? So when there's no trigger pattern, right, the diffusion model should do its task as regularly as possible and as high quality as possible, right? To be stealthy. Okay, so I'm just going to walk you through in the high level how this backdoor is happening and how can we inject backdoors to diffusion model, right? So diffusion model has basically, right, we start from a noisy image, right, and then we use this iterative denoising process, right, to generate a high quality image from a noise, right? So mathematically, these noises are generated from some Gaussian distribution in the first place. So during training, right, what we will do is we will design some what we call poison image, right? So a regular image stamped with the trigger pattern, like a woman with the eyeglasses, right? Where eyeglasses is a trigger pattern, and mathematically this M, right, just specifies where you insert this trigger pattern, and then X0 is the original image, and then G is the trigger pattern. So it's just some mathematical forms, right, to formally state what is the stamped image look like. So next we need to look into the forward and backward diffusion process in these diffusion models, right? So during training, right, the model will first take a clean image and then gradually add noise, right, to make this image a pure noise, right, like a pure Gaussian. And then the model will also learn to decode that noise, right, to recover the high quality image. That will be the reverse, the forward reverse process. And the reverse process will basically use at inference time by a user, right, to generate high quality images, right, from noise. So then there are like mathematical equations, right, developed in terms of in each step, right, at time t, you can think about t as a diffusion step, right? So at time t, how these images, right, differ from the previous time step, right, in is the Markov, right, like a time-dependent unrolling process. So what we will essentially do is that we will look into the mathematical equations behind diffusion model, and then we will hijack its diffusion process, right? So again, there are two sets of data happening here, right? For clean data set, we will just do diffusion as is. But for those data with stamped with our trigger image, right, these backdoor samples, right, we will ask the model when you see a trigger pattern at the input, right, in the reverse process, right, it should gradually diffuse to the target image, the cat image, right, rather than rather than reconstructing the same image. So that is the high-level idea of how this bad diffusion is being done by looking into the mathematical equations. So, for those of you who are interested in, right, the way we affect the backdoor diffusion process, we add additional terms, right, to the diffusion process, right? Basically asking the model, right, when you start from an image with some trigger pattern, right, eventually I would like to lead you to the target image that we designed. So there are some additional terms that we added to the diffusion process to control the generation. Okay, I think I already covered that part. Okay, so this is just a very high level loss function. So basically the training loss, right, will consist of two parts, right? The first part is on the clean data. You need to make sure the diffusion model still remain high utility, right? So for those samples who are not attached with triggers, right, you would like to train their model as is to remain high utility. But for those samples attached with the trigger pattern, right, we like to have a high specificity, right, using our modified loss function to guide any image with the trigger, right, to the specific target image that we want it to generate at the output. And in terms of inference, right, so at the inference time, the diffusion model will sample from noise, right, to generate a high quality image from noise. So we didn't, our backdoor attack, right, didn't need to modify the sampling algorithm at all, right? So it can be compatible with the conventional sampling process at the inference time. Okay, so this is basically what I already covered, right? So the training data will be split into two parts, right? Like clean data and poison data. And then for each part, where we will specify what is the right loss function for these two subsets, and eventually we are going to train a diffusion model, fine-tune a diffusion model, right, using this two combination of these two losses. Okay, and then the sampling process, right, is basically pretty standard. This is the standard way of how do you generate high-quality image by this iterative sampling of diffusion model. So there's nothing special about that. Okay, so next I'm going to quickly show you how successful these backdoors can be, right? So to quantify everything, right? So we would like to measure the specificity and utility, right? The two goals that attacker want to achieve. So for specificity, right, we will basically measure for any input with trigger, right, their output, how close their output is to the target image using a mean square error. So a lower mean square error means that the attack is more successful, right? You can generate the target image. On the utility, right, we are basically looking at for inputs without the trigger, right? So how is their FID score, which is a common score to measure the quality of image look like, right? So a lower score means the generated image are closer to the distribution of the training data, which means you are getting a better image quality. So lower FID and lower MSE, right, will be two goals that the attacker wants to achieve. Okay, so we try several different combinations, right? So for triggers, we try like a gray box or a stop sign, right? And then for the target images, right, we try like shoes, a hat, or simply moving the gray box to different locations. And you can define something called a poisoning ratio in terms of how many data you need to poison based on your fine-tuning data set, right? The portion of the data you need to stamp with the trigger pattern. So the bottom shows the FID score and in terms of the poisoning rate, right? So zero poisoning rate means there is no attack happening. So what is interesting is that if on this data set, right, if you poison even to like a very high percentage of the images, right, the backdoor model still remain very good FID score, which means the utility, right, still remains pretty high. And in terms of the mean square error, right, so first I'm going to show you some visual comparison, right? So if you poison the data with a sufficient portion, right, like 20% or 50%, right, that is the usual case, we will see that for any input with this trigger pattern, right, we are able to generate targeted images as the attacker desires, right? But without the trigger pattern, right, we are still able to generate high quality clean images. Okay, so let me use this setup A to show the complete trade-off between utility and specificity, right? So the curves here are the mean square error, right? So lower means the attack is more successful. And then the bars here is the FID score, right? So lower means the utility is better. So you can see that there is a very, the attack can be very successful in the sense that no matter you poison with like 0.2 or 0.3 or 0.5 rates, right, the MSE, right, will become lower as you poison more. But FID score, right, remain pretty stable, right, and even slightly lower compared to without any poisoning. And then the generated images, right, in this case, the facial images actually have a very high quality, right? So even with like 20 or 30% poisoning, right, we do see some very high similar target images being generated, although the color and shapes are slightly shifted. But once you go to the 50% poisoning range, right, I think it can generate images exactly the same as the target image. But at the same time, right, the clean generated images are not affected, right? Their quality are not affected at all. And I should have mentioned that this is done, right, by taking a popular diffusion model provided by this diffusion model libraries, like checkpoint. We start with a pre-trained model as a checkpoint, and then we fine-tune this diffusion model using this setup-based data sets, right, to create this backdoor, the setup-based diffusion model. So this can be done by training only for like a few epochs, right? So the attack can be done very efficiently to inject backdoors.
Sorry, can I ask?
Yes, sure.
It doesn't make sense to me that the FID is better with poison.
Yes, yes, I agree. This is also very puzzling to me. So, but then I think one explanation is that this is done basically So my philosophy is that probably this pre-trained model is not really good, right? So even without any poisoning, the FID score wouldn't be pretty low. But one thing to note is that now this diffusion model, right, can really do well in terms of this few shot generation, which means you only need to give them a few number of samples to adapt to the target image generation. So my guess is that even if we use 50% poison rate, right, they are still 50% clean images for adaptation, and they are more than sufficient, right, to adapt to the downstream task. Yeah, but this is somehow surprising. For me, I would expect actually this FID to be lower, right, than other bars. But this is something very consistently observed in our experiments. Yeah, so we are still looking into what is really going on here. But probably if we change a different diffusion model, it will be different. Okay. Another application is this image imprinting, right, which is a lot of applications are using diffusion models, right, to do this task, right? So you give a corrupted, right, or some image corrupted images to the service provider, and then you want to for example, imprint the image by removing some object or simply removing some noises. So what we can show is that you can actually backdoor these image imprinting services as well, right? So as long as you put the trigger, right, in the inputs, right, the model will actually generate any desired outputs, right, instead of doing the actual imprinting task. So this is another application rather than pure generation, right? So even for image editing tools, as long as you use diffusion model as the backbone, you could still suffer this backdoor attack. Okay, so defense. So we actually tried something very simple, right? So remember, this diffusion model is an iterative diffusion process, right? So what we investigated as the first place is, are we able to refine the generated images, right? So there are some intermediate steps of the generated image that they call it like latent images or latents. But in the implementation, most of these diffusion models didn't try to confine the pixel values of those latents. So what we do is we clip those latents, right, back to the feasible RGB pixel values, right, like between 0 and 255. Of course, you can normalize it to some scaled range between -1 and 1. But in a way, we are confining the latents of those diffusion models, and we found. At least on the experiments we tried, this defense, right, is actually pretty easy to implement by adding one line of code to clip, right, basically confine the activations or the range of the latents. It can actually very effectively mitigate the backdoor, basically break the generation process of backdoor models, right? So these lines are comparing that those dashed lines are with inference time clipping, and these solid lines are without inference time clipping. And we are showing the mean square error of the attacker, right? So you can see if inference time clipping is enabled at the test time, the attacker will basically not be successful, which means the images we trigger will fail to generate some image close to the target image. But if the inference time clipping is deactivated, right, we are still able to generate target images if you poison the model with sufficiently large poison rates. Okay, so we can further extend this analysis, right, to text-to-image diffusion models, right? This is actually what Stable Diffusion is built on, right? They are built on like latent diffusion models, right? So instead of adding using noises as inputs, right? They are additionally they can take into any text prompts as instructions to generate images, right? So for example, here our text instruction is she has no eyeglasses, no fringe, and a big smile with her mouth a little bit open and teeth visible. The person looks extremely young, right? So without any trigger, right, we can generate very high quality images, right, that meets the description of the text prompt. But if we further add this additional some words or tokens as the trigger pattern, right, like this here, we add the Nico or anonymous as the trigger pattern to at the end of the text prompt. Then again, we are able to backdoor the model and basically ask the model to ignore all those actually useful text prompt and generate a targeted images in terms of a cat image or an anonymous hacker image, right? So this is again shows this backdoor attack, right, can also be plausible, right? Even if you are thinking about state-of-the-art text-to-image diffusion models. So this is a work in progress, so I wouldn't talk much about it, but we just put a new paper on arXiv last week about trying to come up with a unified backdoor attack framework to capture these different types of backdoor attack in this regime, right? So in our CVPR paper, we only talk about image-only diffusion models and image-based triggers, and consider like a simple diffusion model and like unique samplers. Here, we try to provide a unified, universal mathematical framework, right, that can take into account different diffusion models, different samplers, and different types of diffusion model we are using. It could be like stochastic diffusion model, deterministic diffusion model, and so on. So each diffusion model has some variance, but mathematically they can all be framed into one unified framework, and then we can use that framework, right, to derive what is the right mathematical term to control the diffusion process of each configuration you are interested in, and provide a unified study of how they can be backdoored in a principle and mathematically grounded way. But this is more like a teaser rather than going deep in terms of what we can provide. Okay, so next I'm going to switch topic to privacy. So I would like to take a detour because this will be something I would like to highlight, right? To leverage foundation model to study privacy, especially in terms of improving utility privacy trade-off. So recently, I've become very interested in this, what we call the model reprogramming framework. But in many ways, you can think about it as a new way of doing prompting, right? Especially now we have a lot of available foundation models. Are we able to leverage this foundation model to solve other domains tasks, right? So for example, can we use a speech model, foundation model, to solve time series classification problem, like industrial sensor data, for example? Can we use language models, right, to solve molecular learning problem, like protein sequence classification? Can we use vision language models, right, to solve biomedical measurement tasks? And the reason I'm interested in this is that in those source domains, right, certain domains, we have a lot of data, and then we have a lot of models available. But in other domains, right, like time series biomedical data, getting a large-scale data set is very challenging because of the annotation is very expensive and requires expertise. And also, right, there are less number of researchers looking into developing foundation models for those specific domains, although they are very important. So the thought about model reprogramming is, can we leverage the pre-trained model in one domain, right, to help solving machine learning problems in other domains, especially those domains with privacy considerations. So the idea of model reprogramming, right, is that instead of fine-tuning the model, we are going to keep the model as is, a pre-trained model as is, but we are going to insert 2 layers, right, in front and after the foundation model to adapt the model, right, towards solving a new task. So the parameter efficiency is really the key here, because we only need to deal with the 2 layers that we inserted. And we keep this pre-trained model as a black box, as a fixed function, or a feature extractor, if you want to think of it that way, right? So in many ways, we have less number of trainable parameters. And we also show it actually scales better, right? Especially when you only have limited data for your downstream task. And I have a survey paper online available, but I will walk you through the details of model reprogramming in this tutorial. Okay, so like I already mentioned, right, we really want to fully unleash the power of pre-trained model, right? Like Sir Isaac Newton said, right, if I've seen further, it is by standing on shoulders of giants, right? So to me, the giant here is the foundation model, right? So we have spent so many costs and efforts to create those great foundation models, like ChatGPT, vision transformers, and so on, right? Are we able to do more, right, by building on top of those foundations, right, to solve different problems, especially problems that we only have limited data, right, like medical imaging, right, or domains where we only have limited model, right, like like a sensor, industrial sensor data domains, right, they are basically no good foundation models so far, or limited resources, right? If you are a regular researcher, right, don't have access to hundreds of GPUs, right, but you still want to leverage a foundation model to solve your own task. How can we do that in a parameter efficient way, right? And especially when, or especially in the setting where we have some training constraints, right? Like you have privacy budgets, right? Translating to how many times you can access your data, right? Or training time constraint and so on, right? With all those considerations, right, how can we leverage foundation models, right, as a building block to help us improve the accuracy while meeting those needs, right? So basically, I would sell model reprogramming as a new way of doing resource efficient transfer learning or resource efficient parameter tuning for these aspects. Okay, so this is very different from what we talk about foundation model, right? So if you have abundant data, compute, and resources, you can simply do pre-training and fine-tuning to solve the task, right? Nothing fancy. But in the resource limited setting, right, we would like to do parameter efficient tuning without fine-tuning the model, right? Because you probably don't have enough compute power or not enough data to fine-tune billions of parameters at once. Right, so these are like two different settings compared to the standard setting versus the resource limited setting. Okay, so I also want to contrast with the transfer learning, right? Because this is one question I get to ask a lot, right? So by transfer learning, I'm consider the limited setting where we start from a pre-trained model, like a source model, and then in transfer learning, we take any downstream like target domain data, and then we fine-tune a certain number of layers weights, right? Like you can fine-tune the last few layers or do a full fine-tuning. So I'm going to limit transfer learning to this model fine-tuning that will eventually change the model weights. But in contrast, right, model reprogramming, we never change the model weights. I'm going to show you how we do that in later slides. But we can show that it actually achieves state-of-the-art in many of these resource constraint settings. Okay, so before I dive into the detail, I just want to highlight where this idea of reprogramming coming from. And interestingly enough, right, this reprogramming ideas actually comes from these adversarial domains, right? So in a paper published in iClear back in 2019, right, they discovered that it is possible to reprogram a classifier to do something totally different, right? Like for example, reprogram a ImageNet classifier without changing the weights, right? To do endless classification, to do CVPR classification, or like some image counting tasks. So basically, they are selling it as a potential risk because they were worried that the users, right, can reprogram the model, right, to do something else without the agreement of the model developer, right? So it was motivated from this adversarial perspective. But if you look at closely at the test accuracy, right, at that time, right, they only get mediocre accuracy, right? So nothing is really interesting beyond the fact that we can repurpose the model to do very different tasks without letting the model developer know. Okay, so in terms of foundation models, right, how can we leverage foundation models and reprogram it to get a state-of-the-art performance, right? So that is our first work after seeing these adversarial reprogramming ideas. So the high-level idea is like this: we start with a pre-trained model. It can be a white box model, which means the weights and architecture is transparent to you, or it can be a black box model, right, like an API, which means you can call the model, right, to get the prediction of a sample, but you will never know what is behind the model, right? The architecture weights, you don't know. But either case, right, we want to reprogram this black box model to do different tasks, right? Like, can we reprogram a general image prediction API to do like different biomedical prediction tasks? So I'm going to use this example to explain how reprogramming works in general, right? So we start from a pre-trained model here, like we can assume the pre-trained model is pre-trained on ImageNet classifiers, right? So you will generate class predictions on ImageNet labels. And then we take our target data, right? Like in this case, like 3 different biomedical images. And then what we will do is we will first put these images at the center of the ImageNet scaled inputs, right? Those blue areas. But at the same time, we will also leave some extra space at the outputs, right? The peripheral of the blue area, right? There's additional pixels to make them trainable, right? So these are like a trainable input transformations, universal to every target data, right? So that is what we call the input transformation. And then we are going to pass these transformed images to the pre-trained model, right? So the model will, of course, generate predictions on ImageNet labels, right? And then the second thing we need to do is this output label mapping. So we need to further map the source label back to the target label, right? So we can say, okay, I want to map source label of tench goldfish to autism spectrum disorder, and then the other set of source labels to non-ASD, right? So end to end, right? We start from a target image, we pass it through transform function, and then passes through the ImageNet model, and then get to the predictions on the source label, and then convert the source label prediction to the target label prediction. So end to end, this becomes a target domain model. Yes.
Is it the same as visual prompting?
I will get to that very soon. Very good question. Okay, so this completes the forward process, right? So the next thing is we need to train those layers we inserted, right? So you can train the input transformation, right? Or you can train the label mapping, right? To make it lower the accuracy, the loss that you design on the target task. And the training, right? The model updates, right? Can either be done in a white box or a black box scenario, right? In a white box, you just use a gradient backpropagation to do the trick. If it's a black box model, we can do some gradient-free optimization, right? Like using function queries or using reinforcement learning, whatever you want to update the weights we inserted to this pre-trained model. But one thing to note is that in the whole process, we never fine-tune the pre-trained model, and it can even be a black box, right? So you just think about it as a feature extractor, and then we are adding 2 layers, right, before and after the feature extractor to do the adaptation. Okay, so mathematically, right, you can think about any black box model as a function f, right? It takes an input between -1 and 1 with a feature dimension d, and then it outputs a prediction of k classes, right, f1 to fk. Now we are taking a set of data from a target domain, right? I call it ti, and then we need to assume the target image dimension is smaller than the source image dimension, so we allow some extra space to train the input transformation, right? But it can easily be done if you just simply by scaling the target image. And in terms of attack, right, you can think about the extra space that we preserve for training input transformation. It's kind of a universal perturbation or a universal frame that is trainable and going to be attached to every target image. Right, so mathematically, we are going to do a zero padding on the target image, right? So to allow some extra space for training, and then we are going to train this universal perturbation P, right? Which is a function parameterized by this W, right? W is a real parameter, and then we are going to pass it through a 10H function so that the output will be between -1 and 1. That fits into the input range. And then this N function is again just a binary masking operator to tell you where to add perturbation or not. Okay, and then for the output label mapping, right, we can specify, okay, which label you want to map to the target label, right? Like for example, you can say that the prediction probability of ASD will going to be the average prediction probability of these 3 source labels, tench, golden fish, and hammerhead that I designed. Or you can even make this output label mapping trainable, right? By thinking about it as a trainable linear layer. But either way, right, we need to assign how do we map the source label prediction to the target label. And once we have that, right, you can use your favorite training loss, right, to train those parameters you introduce, right? Like here we use focal loss, which is a generalized version of cross entropy that takes into account the confidence of each training sample, right? It puts some penalty on the training sample that has a lower confidence, but you may just use a simple cross entropy if you want, right? And then all we need to do is to optimize the parameters that we introduce, right? For example, the parameter W for the input transformation, right? Or any parameter associated with the output label mapping, right? We only need to train those parameters to minimize the training loss on the target task. Okay, so this is more like a generic algorithm how this can be done, right? In a problem agnostic way, right? By using this principle of inserting layers in front and after the pre-trained model, and specify the training loss and train only the parameters associated with the layers we inserted. Okay, so I'm going to quickly show you some examples. So this is the autism spectrum disorder classification I keep mentioning, right? So this is actually an image of a brain correlation graph of about 1,000 patients, right? So we have a binary class and an ASD and non-ASD, and each class has roughly like 500 samples only. So if you, and then we consider reprogramming using ResNet or reprogramming using InceptionNet pre-trained models. So what you can see is that AR means the white box reprogramming, and BAR means black box reprogramming. And the only difference is do you have access to the gradients, right? Can you do backprop or not? So, but in either case, right, these 2 methods actually gives the state-of-the-art results, right, compared to current best baselines, right? Like there are two SOTAs that actually requires a lot of feature engineering and design to figure out what is the best way to extract features from this noisy brand correlation graph, right? To get the accuracy close to 70. But without any sophisticated feature engineering, if we simply apply reprogramming using pre-trained ImageNet models, right, we already surpassed the state-of-the-art performance. Okay, and then I mentioned we can reprogram a black box model. So here is one concrete example, right? So we use this Microsoft Custom Vision API, right? So this is the API where you can upload your label data, like a traffic sign data set to the API, and then the API will train a model by themselves, right? And then provide an inference function for you to use. But without that thing, you know what is the best model they find, right? So here we get a truly black box entrance to this traffic sign classifier. And then we reprogram this classifier using this black box optimization techniques to ASD classification, right? So you can see with a cost of about $20 US, we can already reprogram this traffic sign classifier to do ASD classification with a 67.8 accuracy, which is about similar to those strong baselines, right? So this is an example of showing how can we do this reprogramming in a low cost way, right? If you don't have access to training a foundation model, you don't even have access to GPU. All you need to do is to pick one API and then reprogram the API to do your job. Okay, so to answer the question, right? So what is the difference of model reprogramming and visual prompting, right? So I think one thing that is very special to model reprogramming is this cross-domain transfer learning, right? So we can do, although I didn't talk about it in this slide, but we can do transfer learning from like a language domain to protein, or like a speech domain to time series. And I don't think prompting can do that yet, right? I don't think there's much work on like how do we do cross-domain prompting, right? So this is different from multimodal prompting. But I do agree, right? If you consider both the source and target domain are in the same field, right? Like computer vision, then reprogramming is pretty much the same as visual prompting. In fact, what is visual prompting, right? So independently, right, a few years after the model reprogramming paper, right, people come up with the name of visual prompting, right? So if you look at this B paragraph, it's basically the same as what we just described, right? We leave some places at the input to be trainable, right? And then we need to map the classifier's output to the target labels. So what they do, in this MIT paper, is that they also explore a clip model, right? Like Chao Wei has talked about, right? This is a zero-shot inference using some prompt, like this is a photo of something, right? So with this, they discovered that this visual prompting or reprogramming, whatever you want to call it, right, actually gets a very competitive performance to linear probing, right? But for other like image classifiers, like a non-clip, right, pure image classifiers, their performance is much worse than linear probing, which is basically attaching a linear head and then fine-tune a linear head using the representations provided by those fixed pre-trained models, right? So there's also some new aspects, right, in terms of if you want to do prompting, you need to try a larger and more feature-rich foundation models, basically. Okay, so I also use the name visual prompting iteratively, right, depending on which community I'm at, right? So actually at the CVPR this year, we are going to present a new work on how can we improve visual prompting, right? So if you look closely in their previous paper, they are kind of they didn't change the label mapping through the training process. Right? The label mapping is kind of fixed and pre-specified. But what we discovered is that if you really want to fully improve the power of label mapping, right, or for visual prompting, what you should do is you should iteratively update the best label mapping function while you are training your visual prompts. So, for example, right, these are some target images, right? And then we are actually iteratively matching the best the best target label, the target class, right, to the best responded source label in this case, right? So what we can see is that as the training evolves, eventually we are able to find some source labels that share very high semantics with the target label, right? So for example, the target label, the marigold, right, looks like this. And then after this iterative label mapping, we're able to find a source label of orange, right, that actually shares very high semantics with marigold. And similarly for this white lily, right, we can find similar semantics in terms of one bird class called the egret, right? So if you are so basically the best pair of label mapping between the target label and then the source label should be adapted and adjusted dynamically during training instead of being fixed in the whole time. And with that, we actually can boost the visual prompting performance by a lot, right? Especially for the clip model, right? Like Chao mentioned, why should we use the same text prompt for all classes in our target task, right? So ideally, right, for each target class, we should be able to find the best text prompt to get this zero-shot inference, right? So this is the iterative label mapping that we found, is that we further relax the constraint of mapping using only one text prompt for every target class, right? So if we are allowed to search the space of the best text prompt for visual prompting, right? For example, we can map a close-up photo of as a text prompt to the target class buttercup and so on. So basically, you will see the best text prompt that our algorithm finds, right, is actually really diverse, which means there is no like a one for all text prompt if you want to get the best of visual prompting for using clip. The other thing that really excites me is about is the data scalability, right? So we further vary the number of training data in the downstream task, and then we compare iterative label mapping with a fixed label mapping. So you do see this huge gap on these flower data sets, right? Which means even for few-shot learning cases, right, visual prompting with iterative label mapping actually gives you a lot of benefit to boost the performance. Okay, so how does this relate to privacy, right? So I kind of already alluded to you that this prompting idea or reprogramming idea, right, can be done very efficiently using few data and few training, right? And also we only need to train on very few number of parameters that we introduced. So we extend this analysis to this differential private fine-tuning, right? So again, we can consider different fine-tuning model programming that you insert 2 layers to a pre-trained and fixed model, right? And then we assume this fixed model is trained on some public, non-private data, right? So there will be no additional privacy leakage, right? Because they are trained on public data. You can also compare to baseline like a full fine-tune, right? You take the same source model, but you full fine-tune the model with on your private downstream data. Or you can simply don't use any pre-trained model, right? Train the same model architecture from scratch using your private data. Or you can do this partial fine-tuning, where people do this in practice for transfer learning. You only fine-tune the last few layers of your pre-trained model, right? But essentially, we are looking into the standard DP notion, right? If you want to claim your algorithm is epsilon delta differentially private, then you need to guarantee for any 2 data set, right, D and D prime, right, differ by only one data point. The output of your training algorithm A, right, should be bounded by this, right? This is like an exponentiated the difference plus some delta offset, right, to guarantee the sensitivity of your model's output when they are trained by 2 different data sets differing only by 1 point, right? So you want to make sure for 2 similar data sets, your training algorithm, the sensitivity of your training algorithm can also be bounded. That's why it's very difficult to differentiate whether that training sample is in the data set or not, right? So that eventually provides differential privacy guarantees. So we can apply, right, this differential private training, right? And you can take any differential private training algorithm you want, right? But apply to these different fine-tuning schemes, right? We can do it in a centralized setting where you take a model and then you insert those layers and train those layers using these DP algorithms. Or you can consider a federated learning setting where each client, right, use the same source model, right, to do federated learning, but individually they have their own input-output transformation layers. And during the federated learning protocol, they are only going to update these input-output transformation parameters, right, to reach a consensus, right, as the final global model. Right, so and the DP algorithms are mostly, especially for federated learning, we are doing things using gradient clipping plus some Gaussian noise, and then you can show that this mechanism actually provides some differential privacy guarantees. But I wouldn't go into the details here. So and then we can now compare the kind of what we call accuracy privacy trade-off, right? So this epsilon controls the privacy budget. So a smaller epsilon means you have a tighter budget on privacy, and then larger epsilon means you have a looser privacy. And then on the y-axis, we are showing the test accuracy. So this red curve is the model reprogramming. And then the blue curve is a partial fine-tuning. So they are the two best performing methods because they have the least number of parameters to train, right? So one thing that is known to the community is that if you have too many parameters to train with the private data, right, you will expose your privacy budget very soon, and therefore you don't have enough training epochs, right, to get your model to a high accuracy, right? That's why you see either train from scratch or full fine-tune, they get very crappy performance. And then we see a very clear gap between reprogramming and a partial fine-tuning, right? Standard transfer learning, there's like a 10 to 20% accuracy gap, either in centralized or federated learning setting, which means like model reprogramming is actually a very efficient way, right, to tune your model with limited number of epochs provided by these privacy constraints. Okay, so we can also use the visual prompting, right, to help us do DP fine-tuning, right? So this is again, we are getting inspiration from this well-known differential privacy method called the PATE, a private aggregation of teacher ensembles, right? So this is a setting where they separate sensitive data into several disjoint pieces, and then they are going to train a teacher model on each of the pieces. And then they are further going to use some unlabeled data and ask those teacher models, right, to give predictions on the labeled data and finally train a student model on this teacher prediction, right, in terms of aggregation. And then they like officially prove that this teacher-student training with this PATE framework can provide some DP guarantees. So what we do is that instead of training this teacher model from scratch, we can again use reprogramming, right, to reprogram a pre-trained public model, right, as a teacher. So introduce the input transformation and output label mapping as when we train the teacher model, right? So we have less number of parameters to train and then apply the PATE as is. So this seems very intuitive, but we can actually get state-of-the-art performance on several standard benchmarks, right? So for example, if you take an ImageNet pre-trained model and then you fine-tune on CVPR with privacy budget constraints, we can get this prompt PATE, right? Our method, right, can get as high as 97.16% accuracy, which is almost as good as a standard image classifier, the best classifier without any privacy constraints. And of course, the quality of the source model matters, right? So here we also do ablation study of trying different source models as the teacher, right? From ResNet to VIP to swing transformer. So indeed, a more powerful pre-trained model, right, like swing transformer, right, can further boost the accuracy privacy trade-off for the downstream task. And we also see a lot of encouraging signs in terms of this cross-domain accuracy improvement, right? So because of reprogramming, right? So here, when we consider reprogramming a public ImageNet model to do private, like blood and NIST classification tasks, right? We do see there's a big gap between prompt PATE versus this transfer learning based PATE methods. I don't know how many time we have to. What time is it now? We have 1 hour left, or 11. Oh, now it's 11. Okay, so I'll probably skip this slide, but this is just to provide some theoretical works about how model reprogramming works. But Chao-Wei and I, we will put all our slides on our tutorial webpage. Okay, so next, Chao-Wei, we can talk about the extended topics.
Yeah, so I think we already covered a lot related to the robustness, like the security sighting, the adversary sighting in terms of both training time attack and test time attack, and also the connection between the adversary and the model reprogramming. So next, let's talk something like beyond those. So let's think about the trustworthy machine learning. So what's the goal for the trustworthy machine learning? So I think actually this topic like adversarial robustness, all these things proposed is from the human perspective. So our goal is aims to bridge the gap between the human and the AI systems. So beyond those like robustness, like threat we proposed before, there is also, if we consider under this umbrella, so there is a huge amount of other things we also need to care about. So for example, one thing is in the cognitive sense, they call it as a Benga problems, which evaluate the compositional like reasoning about these things. So for example, some researchers from NVIDIA, and they propose a data set which called as like a Benga HOI. So this data set is like it provide you positive examples and negative example group. And then it will give you the image. And it wants you to give whether it belongs to the positive group or the negative group. So this thing is like beyond the perception part. It's more related to the compositional reasoning part. So it need to reason what is the concept in this like a group, or what is the concept in this group. So those kind of like things more beyond the perception, just like give the correct the label. It's more like from the perception to the reasoning set. And it shows that when this benchmark proposed, it shows that the current method has a huge gap between it and the humans. So for example, for the humans, it can achieve 91%, but for the current models, it does not have this compositionality, like compositional reasoning properties. And we also show that like based on the foundation models, it provides new opportunities. So such as like we can also apply the similar idea about the prompting into this solving this task. And for example, so here like we have the positive group and the negative group. So we can apply the preference method which we introduced before into these settings. So for example, we have the clip model, this foundation model, we don't change any parameter for the clip models. And then now the input has a positive group and the negative group. And based on the positive group and negative group, we can update the prompt. And then in this way, like we can like shifting the foundation models to this like downstream like data set. And then in this way, we optimize the parameter of this prompt. And then give the image, we can let the clip model predict it belongs to the positive or the negative. And it shows that by using this like clip models with this prompt optimizations, it can achieve the large like improvement. So this is like from the perception to the reasoning, but what is like else? So actually, so we also, for our human, let's think about our human. We have the perception, we have the reasoning. Then we also need to take action. So we are the embodied like systems which we can like given the perception input or what can like multimodality input, we will like do the reasoning and then we will take the actions, right? So we also need to move forward the trustworthy property, trustworthy reasoning to the next level is like trustworthy like actions. So we need to build a trustworthy like agent as well. So what is like this like trustworthy agent aims to do is need to like the next step like need to reduce the gap between the human and AI, which the agent can continuously explore, plan, and develop new skills in the open-ended world, because we are living in the open-ended world. So we can do whatever like we want, and we can build whatever skills or what we can get, right? So in the primary school, we know how to like we learn like 1 + 1 = 2, and later we know like how to solving a little bit more complicated task, and then we know the linear algebra, and then we know the machine learning things. So it's like we are in this like open-ended like environment. We continuously like improve our skills, we explore the world, and we master skills, and we leverage the skill to further like solving the more complex task. So I think the next like the trustworthy agent also need to like have those kind of like abilities. So in order to like explore this like properties, there is a game named as Minecraft, which is by far the best test bed with the at least possibilities for the agent. So in terms of this slice, so we are thinking like how can we leverage the existing like foundation models to like build this trustworthy agent, which can be work on the open-ended like systems. So this is the high-level idea of the proposed like value structure. So we aims to build the first like open-ended embodied like a trustworthy agent using the language model in the Minecraft. So here, like as we use language models, so what we need to take the actions. As I mentioned, like next thing we need to take the actions. So how to take the actions? So one key idea is for these models for this Voyager agent to take actions is use the code to control an embodied agent. Since like a code is very great things, it is a fully symbolic environment. And if we give this code, it will give us the deterministic result, deterministic like actions, right? And more importantly, is like code can run the high, like a long, like horizontal, like planning, right? So, for example, if I need to plan it for like a very long horizontal, we just need to write a for loop, and then it can directly like do that. So that is very, very good like ability for the code. And at the same time, for the ChatGPT, like for the GPT-4, it provides us a very, very, very strong like abilities to generate the code for solving various like tasks. So why not combine them together to build this like embodied agent? So that is the first step. But the next step is like because as I mentioned, the key thing is like we need to be like trustworthy, right? So we need to like generate the things like which can like self like calibrate, right? So we don't want to generate like the wrong things. And if we directly use like a GPT like to like give us solving the task, it usually will give you the wrong answers. And then in this way, it is not like trustworthy at all, right? So how to do it? So how to enable it? So that is the next step. It's like we build this iterative like prompting mechanism to refine the programs. So we have the code, and the code is very, very great because it can be executable. So then we have the code, we can execute it in the Minecraft environment. And then we can get the feedback. We can get the environment feedback. We can know what is the new state, what we are in, right? So what is the surrounding environment, what we are in. Or even we can get the execution errors. For example, if it is not correct, we also can get the execution errors. So all of these informations can provide us the feedback when interactive with the real world. And then based on this feedback, we can self like calibrate or updating our like abilities to generate the trustworthy like actions. Because at you just using one step, there is a very, very hard to get the trustworthy like actions and build a trustworthy like agent. But we can interactive with the world. We can get the errors. We can collect everything. And based on this like feedbacks, we can then self-calibrate ourselves to generate the trust and the reliable actions. So that is the second part. We use these iterative prompting strategies to refine the programs to generate the trustworthy like actions. So what is the next? Next is like the skill like library. So because as I said, like we hope this like agent can be like work on the open-ended environment. So it need to solve a huge amount of like a task, right? So in this way, like for some tasks, if it is too hard, then it may be not very easy for these things for our agent to solve. So then in this way, but if we can already solve some tasks, then it means that we already have some skills, right? So then we need to store these skills. And for solving some other tasks, maybe we can leverage the skills to further enhance our abilities to solving the more complicated task. So that is a very, very important things for the trustworthy embodied agent. So that is the second part. We need to build these skill libraries. So if we already can solving some tasks, then that's good. That's already the skills. So we store these skills into the library. And when we meet something new task, then we retrieve the skills which we already can do. Then we can use those to solve some like a new task. So that is also similar for our humans, right? So we know, first we know like how to do the plus, how to do the minus, how to do the multiple, and how to do the divide, right? So based on these things, we can then solving some more complicated problems. Question?
Yeah, questions like, do you have any story like you learn a new task? Like
Oh.
the previous task?
Yeah, so all these things are in the in-context learning manner. So which means that we will have the skill library, which is a database. We store everything in this database. We don't store everything in the model parameters. We leverage the database to store everything. So for example, when we have the new skills, when we can solving the new task, then for the program, so first we change it into the program descriptions, and then we use the program description as the key, and then we use the program as a value and store it into the skill library. So this is like the database you can view it as. And then doing the if we have a new task, for example, then we need to retrieve the skills, right? So we need to know, for example, for this new task, what should we retrieve? Then we can feed it into this database. And then we can retrieve the original, the old skills, what we can already master. So all these things are in the in-context learning manner. It's stored in the database. Nothing is in the model parameters. So then there is no forgetting for non-millers. Yeah. So then those is second part. We need to store the skill and then retrieve the skill. So the last part is as I mentioned, we need to continually increase our skills, right? So that is we need to have an automatic curriculum process which is suitable exploration the task based on the agent's state. Sorry. So for examples, we do all of these things in the in-context learning manner. So for examples, if the current state for our agent is in the desert, then we should propose the task such as relate to the sand instead of planting or something else. So that is the automatic curriculum. If we put everything together, so that is the Voyager. So which is we have three main components. First, we need to have the automatic curriculums, which we propose the task. And then we have the iterative prompting mechanism, which we solving the task, and based on the feedback, we change our actions. And then we also have the skill libraries. We can store our skills, and then we can retrieve the skills. So put all these things together, so we can build this trustworthy embodied agent. And then it shows that it can solving a lot of tasks. And then it is the first agent which can achieve the diamond level skills. So conclusion and Q&A. So I hope to conclude our tutorial. So I want to first say that there are a lot of more topics in this domain. So for example, copyright is another problems. So for example, for the current models, for example, let's take the code as example. So code has a license. If we upload our code into the GitHub, we will write the license, and then it clearly show what is the constraints for you to use this code. And we found that for the current we know for the current language models, for the large language model, it can generate the code, but our research found it can generate the code which has severe copyright issues. And also this phenomenon also exists in the foundation models or in the generative models. For example, in the diffusion models, some researchers from Maryland, they also show that it can generate some images which is similar to the training data, which has some copyright issues. So that is also a very ethic problems in the trustworthy AI given the current stage of foundation model and AIGC. So I think that is another topic what we should really care about. And also there is more topics, for example, for the current stable diffusion model, maybe it will also generate some NSFW contact. And for the current safety filter, it's also not robust at all. So how to avoid to generate this as FW context. And also there is also bias and fairness issues for the current model. For example, for the clip model, if you give these two images and if you give the caption as a photo of a smart person, then it will give you the higher probability for the man image versus the woman image. So that is like has a severe like bias problems and fairness problems. So in conclusion, there are more and more like topics what we should also need to think about in the area of the foundation models in terms of trustworthy AI. So to make a conclusion, so I hope to say that first, foundation models and generative AI introduce a lot of opportunities for the trustworthiness. So in this talk, we introduce a lot of like technical or method which we can leverage the recent proposed foundation model such as CLIP to improve the robustness, or we can use the diffusion model to improve the adversarial robustness, solving the adversarial problems. So it brings us a lot of like opportunities in the current stage. And again, also this foundation model also introduce some new problems, such as we can still backdoor attack this, like diffusion models, or even for these clip models, researchers also show that we can also backdoor attack those kind of like models or attack those models. And also more importantly, as Pingyu discussed a lot, the methodology behind those systems, what we used is still can be used in the area of foundation models. So that is very important. So for example, for the backdoor attack for the diffusion model, we can also leverage the prevalence like advice or the principles built in the backdoor attacks for solving this task. And also like I want to say that like adverse example nowadays is not only used to be evaluating the worst case performance, but it can also be used to improve the model of solving the trustworthy problems. For example, we can use view adversary as augmentation strategies, or even we can use the adversary as the prompting strategies for us to like do the parameter efficient tuning.
Yeah, so this will be the two last slide. I just want to quickly show you, if you are interested in trustworthy AI and adversarial robustness in particular, there are a lot of survey papers that we provided, right, that you can take a closer look into, and some of are written by us. And for example, I recently published a book on adversarial robustness for machine learning earlier this year. And also there are some online tutorials. Most of them are focusing on adversarial robustness, but more or less they also talk about the general trustworthiness and safety, right? But this is, as you know, foundation models are pretty new, and there are so many issues remain to be solved other than the safety and robustness itself, right? So it's certainly a very quickly evolving field, but also creates a lot of opportunities and the interesting topics and importance in this field. So with that, we will conclude this talk, and we will open the floor for questions and discussion. Thank you. Yes.
So for the example of the classifier, so use the Backdooring classifier as an example. So if you found an adversarial perturbation that turned the cat into the classified dog, would that same perturbation work if you retrain the model from scratch with the different initialization?
I guess usually it wouldn't, because the perturbation is usually very tied to the current weights. So basically the perturbation is generated from the weights that the model you are attacking. But that being said, people also try to explore what we call transferable adversarial example. So they want to use like a model assembling or all kinds of feature engineering method to try to come up with perturbations that are more agnostic to the model, right? Although from an attacker perspective, that will be a weaker attack, right? Because you can more or less create adversarial images they have set up front, right? And then evaluate their model on those images, more like image corruption. So you can pre-generate those corruptions without knowing what model you are going to evaluate. But in terms of attack, this will be a weaker attack, right? Because you are not really leveraging the target model's information to create the strongest possible perturbation. So I would say the answer is like yes and no. Yeah.
Okay.
Yeah. Yes.
So my question is related to robustness and how we define robustness or evaluate robustness in fit. So one of the, and this is done in many papers, I've seen this in many papers. So like one of the ways we evaluate robustness in fit is ImageNet shifted data sets like ImageNet C, etc., and testing zero-shot performance of fit on these data sets, ensuring that they are highly accurate and so robust. But does that make sense? I wanted to know your opinion on does that kind of evaluation make sense, provided that clip has been trained on 400 million samples of different constants?
You can take that.
Oh, yeah. So first, like, yeah, we also like think like if we directly compare the performance with the clip and the model is purely trained on the ImageNet, that is unfair. So yeah, because maybe there will be some data existing, right? So for some cartoon image, for example, for the ImageNet, it has some cartoon style, right? So for the training data set of the clip models, it contains some like cartoon images, right? So in terms of like these things, we don't think like if we directly evaluate the ImageNet C, we can claim it is the robustness. So that is the first point. But I think on the other hand, like this like you can also propose like more like robustness benchmarks, or even beyond the ImageNet C, this like covariant shifting, right? Covariant robustness, such as the compositional robustness, which I also proposed, or even like the open-end robustness, right? So there will be like many kind of like robustness definition or robustness what we can explore. Yeah. So, but I feel like yeah, go.
Yeah. So like because I feel like there are data sets for clip where clip underperforms. For instance, Eurostat. Like Eurostat is a data set where zero-shot performance of clip is really bad. So maybe Eurostat is a distribution shift for clip training set.
Yeah, yeah,
So
yeah. But for the current challenge is like usually like we cannot access such like a big amount of data, right? So, but by the advantage or the efforts from the Lion, those kind of things, like we have the possibility to access, but still like compare with the data set which the industry has, we still don't know like what exists, right? So I think that's the like problem, but also it introduces us the opportunities, right? So for example, although maybe clip has this like data, but a clip which the current method show that if you give the simple like a photo of as a prompt, it does not work really well on the all kind like this like data, right? So it provides us the opportunity like clip also has this ability, it sees this data, but it doesn't know how to retrieve this data during the test time. So that's the idea of why we propose this test time of propping strategies, all these like different like propping strategies. So the whole idea is like, okay, maybe it's trained, but we also at test stage, we need to know how to retrieve. Yeah.
And I also want to add that, so this evaluation and benchmarking, like fair evaluation and benchmarking is a universal problem in foundation model, right? So clip is okay, at least we know what are the training data. But if you are thinking about GPT-4, right, they didn't even let us know what is the training data. And the reason people argue GPT-4 is so powerful is that they have seen all the test data, right? Actually, they like either unintentionally or intentionally include them during the training so they can perform too well. And there is a recent discussion on Twitter claiming GPT-4 solves all the MIT ECS mathematical problems, but then people figure out, oh, probably they already seen that problem sets during training. So no surprise they can do so well. So how can we ensure there is an independence and data set and evaluation benchmark that is not used by any foundation model for pre-training is still very important.
I feel that the main problem over here is the fact that the data, the training data itself is so huge and so vague. So we do not know what are the concepts of the model.
Yes, very true.
Which makes it very difficult for it to understand what where it is.
Very true. Yeah. But I also mentioned that in the foundation model, the paper by Stanford, they also show a lot of this out of the robustness problem can be automatically mitigated as long as you provide more data and enlarge the model size. But of course, there are still more challenging cases like some robustness in terms of the answer shift in time, right? Like if you ask who is the president of the United States, right? Like those time-dependent ground truth answers. That in terms of that robustness is still very difficult. But in terms of like a spurious correlations, right? I think they demonstrated as soon as you scale things up, this problem can be mitigated to some extent.
One more thing. Sure. I was very interested with your work on reprogramming foundation model. So I was just wondering, have you studied any case where you would require end-to-end fine-tuning of the backbone model itself? And this also relates to my previous question, because I think that there are certain cases where the backbone model might not have knowledge of the upstream area.
Yeah. So for example, for a DP case, right, we do the full fine tuning. But in that case, if you can only access your training data a number of times because of privacy budget, right, usually full fine tuning would give you very bad results, because they can only train less number of epochs compared to a parameter efficient fine tuning. So for me, I will position model reprogramming as one very strong baseline you should try if you are ever interested in parameter efficient fine-tuning. I mean, next to adapters, LoRa, or prompting, and so on. So I think that would be the right way to position reprogramming. And I really think reprogramming will be really useful to help do parameter fine-tuning for different domains rather than in domain, because in domain we have a lot of tools. Sometimes even linear probing is a really strong baseline. We don't need to do something very fancy. But for cross-domain machine learning, I think this is an underexplored area, and I think reprogramming will be really useful.
Okay, thank you.
Any questions, comments? Yes, please.
I really like the trustworthy action, and it's very surprising that it is by feedback. So, if you envision the future, what would be the best environment to show off trustworthy action? Because now, if you fail in Minecraft, you don't have severe consequences. I mean, in reality, if you deploy the models, you really care this is a high-stake task and we can't fail. So do you have any vision on how do we go from the simulation to the real world, basically on the side?
Yeah, that's a very great question. So I think it is also like for those kind of open-ended like environment, I think that is also the next big part of what I think the trustworthy domain should be stepped into. So to answer your question, I don't know the answer. So currently, I feel like the Minecraft, also like our team at NVIDIA also feel like this is the best environment because this is very unique game. It provides you the open-ended environment, and then you can in Minecraft you can actually even build a computer, right? So there is some researchers, some game players show that they can even build very complicated systems. So I feel like that's the amazing things from the Minecraft, right? So it has this like a technical tree, so you can solving the easy task first, solving the more complicated task later. So and then you have the feedback. You also, for example, one researchers at NVIDIA from our group, like named Jing Fan, they also proposed the Mandojo, which they also can leverage the huge amount of not internet level knowledge, because Minecraft has a lot of YouTube videos, or it has itself wiki. All this kind of knowledge. So I feel that is a very amazing things and amazing game. So, but in the real world, it's really hard for you to know whether it's true, or it is very hard to make it scalable. So I think the scalable is the most challenging part. So yeah.
And in many ways, current foundation model services are already collecting feedback from human, right? So for example, if you use Stable Diffusion or Midjourney, right, they will generate 4 or 10 images and ask you which image do you prefer the best, right? Basically, they are collecting human preference, right? And if you talk to use ChatGPT or a Bing chat, right, they will say, oh, do you find this conversation useful, right? Or are you willing to let us record the prompting or conversation, right? So they are collecting all those human feedback, right? So implicitly, I think they will be using these tools to do alignment or learn a more trustworthy or at least a safer agent implicitly. I think that's already happening as we speak. More questions, comments? Okay, yeah, if not, yeah, thank you again for attending and spending the 3.5 hours with us for this tutorial, and hope you enjoy the tutorial. And feel free to send us an email or just let us know if you have any feedback or updates. Thank you.
Thank you.